So in some samples, the compounds had a certain retention time, and in other samples, the same compound has a totally different retention time. And that was a shift like 4 minutes, some cases 5 minutes. So something was clearly wrong. One of the things in your work, especially on this instrument, is that you really have to have robust retention times. You have to have a confidence that the same compound will always show at the same retention time. So we thought, okay, what's going on? And then I don't know who it was, but someone discovered that the inlet tube on the LC for the pump was not actually submerged in the bottle. So it had come up above the level of the liquid, and that can cause, of course, then that there is no input of that solvent, and perhaps cause this retention time shift. So we purged the system, and we ran everything again last night. And so here's the data. You can see the batches here, and we have all green check marks. So what we'll do now is we'll just go back to analytics, and we'll process this data with the method that we used yesterday.
ألو صباح الخير، كيف حالك فادي؟ رامي معك، شو أخبارك؟ تمام؟ ماشي الحال؟ اتصلت فيني الصبح أنت يمكن ما هيك؟ بس كنت تسألني على السكيل، صح؟ هيدا we need a scale على ال critical point dryer. We have this machine and we need the scale تيكون تحت ال CO2 tank حتى ينعرف during the run إذا فضيت ولا still فيها to continue the run. 100 kilograms. Yes. Well, the run, I'm not sure. Finish of life. How much does it consume?
When we processed the data yesterday,
صراحة يعني سألت أنا جوان ورانيا قال ما كان موجود سكيل وانتزع وتجنزر وانتزع وكبوه ما رجعوا جابوا غيره، واكتشفت أنا بالصدفة إنه المفروض يكون عليه سكيل، يعني جاي مع الماشين المفروض إنه to have a scale. لا ما في، لأن ما في عليها هي تانك لأنه ليكويد جوا CO2 ومحطين له الريجوليتر برا تعرف قديش فيها جوا. شو؟ well لا بلا the empty cylinder we can know it from the company. it varies صح. ما هو كمان في يعني في another option is to have it complete وبتشوف قديش عم تنقص. يعني هن السكيلز بيجي في عندهم two options، يا اما بيحسب لك تير as the empty bottle you input it انت بس we can get this هالinformation بس we can get it from أشهاب وفينا نلزمهم نفس الأنيمة every time. usually these balances allow you to either do two options، يا إما بتحسبها مثل ما عم تقول إنه empty bottle بعدين وقتها تنملأ شو بصير وزنها وبتحسب التاع على empty bottle or بتاخدها with the full mass empty bottle plus the CO2 بتشوف لك قديش عم ينقص. Okay. لا ما هو ما هو عملنا اياها بطريقه انه في بيعليها شيء يعليها بيحسب لنا الناس، يعني it's not being loaded على السيل all the time. لا هي حتكون عادي على بلاتفورم اجى شرح لك كيف بتكون، وبعدين في لا يعني الليفلر عفريت سيارة او شيء هيك بتعليها شيء تعليها بالقطع البالانس اللي بيكون جاي من فوق. حيكون معلق ببلاتفورم تاني فوق التانك، يعني ما حيكون اندبندنت من السقف. صح، جاي فوق التانك وعليها البالانس، وشينا شغله نحن ساعتها بيمسكوا البالانس. بس صراحة اكشلي انا لان هلا يعني نحن اخذنا اوفر من عند هيدا، بس انا ستيل وديتها للبروكيورمنت تشوفوا لنا اذا في حدا ارخص، واعطيتهم جنريك سبيكس للبروكيورمنت. عرفت علي ايش عملت؟ ايه عالي دولار، بده ياخذ دولار هو، لان هو شركته هيدي بدبي اكسترنال يعني. لا مش هذا، واحد اسمه اتش او كي تريدينج، هو عنده شركه هون وعنده شركه بدبي. صح صح، تفاجأت انه المفروض انه يكون في عليها ومحطين ومصاري. عم يعني امرها بتكون during the run توقف، وبدك ترجع تعيد يروز ذا سامبل اللي جوا during drying. وشاف كرمال انا بعتها البروكيومنت لان شفت غير مودلز انا صراحه فيهم ترك التانك عليها ويدوت لوز اكيورسي وموجودين، فعشان هيك انا بعتها للبروكيومنت خليهم يعملوا شغلهم ويشوفوا لنا اذا في شيء باتر اوفر كمان. ايه لا it should be accompanied with a balance. قريت عنها انا شفتها. قال اذا بدك تحط ريجوليتر بيساعدك بس still you will need a scale under the tank. هيدي بدي اشوف لك اياها. ايه شور alright اوكي ماشي alright هلا اسمي باي واتساب. اوكي باي باي.
Right, so they're all up there around 7 or 8, nothing is too long. Okay, so everything else is fine. I don't need to go through the other settings because they're the same. I just want to use the same settings. So I'll go ahead and I will say save. So that will save and overwrite that method now with the new retention times. Then I will save process. So if you missed something or I'm going too fast or you didn't make the connection between what we're doing yesterday and today, please ask the question, okay? Don't sit and be frustrated or something. If you have any question, just interrupt, come off mute and ask the question. You really have to understand all of the steps and also try to grasp my thinking as I'm going along. That's why I try to talk a lot about what steps I'm doing and why I'm choosing a certain thing when maybe it's not clear why I chose that. Okay, so the processing takes a little bit longer this time because we have more samples, right? Now we're processing 25 samples. So now we're going to have a bigger result table. Yes, and you see we have all the samples there on the left side. Okay, so again, I don't like this layout, the default layout, so I'm going to go, first thing I always do is organize my layout. So I have the one that I like here. I have everything organized how I like it. So what we'll do is we'll go through the B samples, right? Let's leave the A samples for right now because the A samples we know it's kind of cheap, right? But we know that the A samples are not spiked with these compounds. So what we'll do is we'll take a look at the B samples. All right, so that's great. We have all green check marks, but we don't have any library data. We don't have any library data because this is the TOF MS sample, right? So these samples here, first injections, these samples were collected with the TOF MS only. So there was no MSMS this method. So that's why there's no MSMS over here. You see on the right side. So we have all green for the other three parameters, and those parameters they come from the MS information, right? Mass error comes from mass spectrum. Retention time comes from the XIC. Again, that's from the mass spectrum, and isotope confidence comes from mass spectrum. Let me just make the chat visible here to myself. Okay, so also if you have a question, you can write it in the chat too. I'm looking at that. I have that page open on my other screen. Okay, so we're just going to go through now, and we're going to check all the B samples that we have good retention times. Yes, look, we do. Okay, so that is great. So I'm looking all green check marks. This is now the second B sample. Here's the third B sample. Yes, we have much more stability. All right, so that was the problem, I guess, is that the little tube slipped out of the solvent. So it was not submerged, and we were not pumping solvent A during the run. Again, that's something you're going to have to watch, especially perhaps those of you not so tall, because those bottles are way up on top of the pump, and they're also in that tray, and the tray has that ridge on it, so you cannot see the bottom of the bottles. So when you are doing this work, maybe you want to get a little step stool or something, and then you can easily look up where the bottles are and make sure that the tubes are always submerged. That is one of the, let's say, little bit drawbacks of this HPLC, that the bottles go on top. And please keep the bottles on top. Don't move them to the side or down below. The bottles need to be above the pumps so that gravity is providing heat. So that is a little bit unfortunate, but you can just keep your eye on it. Okay, so we just continue through. So we have now the first IDA sample. Okay, so I'm just going to check retention times first. So retention times are good. All right, so this is really excellent quality data we got here now because we have stable retention times. Yes, I'm just looking at this green column here for retention time. So all the B's are green. Okay, super. Okay, so now, all right, that's very good. Okay, so let's go back to the IDA. Here we go. So if you remember, we also talked about having this red circle for the library confidence for two of the compounds. And those two compounds are isomers of each other, prometrin and terbutrin. You can see that they have the same formula. You see they have the same formula. And they have, by definition, the same exact mass. So they have the same TIC. So actually, when we look at this data now, we do have another problem with this. I don't know if you caught it, but here I'll show you the prometrin. Here's the prometrin. So that looks good, right? Everyone see that? I have 4 greens. Good mass accuracy and good library match, and not just relying on the green color, we're also taking a look at the purity. And here you see that we have all 3 scores are good. And now I'll show you the terbutrin. So this is the other isomer. Can anybody see the problem? There's a little bit of a problem in how we set up the data here in the data analysis, specifically the integration.
Oh, we took the left side.
right?
Should for the therapy train the right side.
Exactly. So the peak has jumped to the same right side as, I'll just go back and show you, so those of you who didn't catch it, right? Here, it's on the right side, so terbutarin actually needs to be on the left side. You can see that we have a bad library match. Why do we have a bad library match? Because it's doing it by the name. So it's trying to match terbutarin to terbutarin in a library, and it did find it. However, that peak is not there, 200, right? The 200 peak is not there because the 200 is characteristic for chromatrin, but the integration is stuck on the wrong peak. So it's giving the bad library match, though it's the same data. So what do we have to do? We have to move it over to this peak on the left. Now, see, we start to have a little bit of a problem here now. Even our peaks are a little bit too narrow. So I don't know if you caught that as well, but here the data points are less than yesterday. And that probably makes sense because yesterday we were not doing great chromatography if the A solvent was not pumping, right? So probably we didn't have the best chromatographic conditions, and so the peaks were a little bit wider. So now, fix the chromatography problem. Now we have narrower peaks. So you can see that, right? The peaks look a little bit too triangular. So we will have to go back and adjust our data points a little bit. We could also reduce our chromatographic performance. For example, we could lower the flow rate. We might do that. We might lower the flow rate, and then that'll lower the pressure a little bit, and then we'll get slightly wider peaks, and that'll give us enough time to have enough scans across the peak, enough data points. Okay, so let's try to move it to the right side. Left, right, yeah, right side. Okay, so the first thing you can try is to click and drag across that peak and see if it'll jump. Yes, it did jump. Right, so expected retention time, you see it changed. So it went over there. However, unfortunately, don't forget this is IDA data. Now we have another problem. We talked about this in the lecture, right? What's happening here? There's no MSMS. So unfortunately, there's no MSMS because IDA criteria didn't choose the second peak to do MSMS on. And we'll come back and we'll talk about that in a second and see what we can do. In the meantime, let's try to force these retention times to be correct. So if you remember, chromatrin is the first peak, so 8.32 and 8.32 is correct. And now terbutarin, I've changed it, right? 8.4 and 8.4. But if I go to another sample, let's go to another sample, you can see it's also not correct. Terbutarin is the first peak, and chromatrin is also the first peak. So actually what that means is, in my processing method, I have the wrong retention time for terbutarin for every sample. So there is a way to fix that without going back to the method, the processing method, and I'll show you how to do that now. So this was the sample that we were working on, where we fixed it, right? So chromatrin here is 8.3, and terbutarin is 8.4. So what you can do when you've made a change like that, and this is actually really important, so you want to mark this down in your notes. You want to right-click, and you have the choice here, Update Processing Method for Component. So if I make any change in my processing parameters, or let's say in my integration parameters, and I want to apply those to all the samples, or even to this processing method, I can right-click and I can say Update the Processing Method for the component. Now you have to do this for each individual change you make.
خبري
Here we made
بتمنى
one
منك
change,
إنه
which
كلام
was
بيناتنا
changing the
هون.
retention time of Terbutrem.
تتذكر وقت
If
دقيت
you
لي
then
تليفون وقلت
change
لي
the
انطي في
retention
اللاب
time of another
وبعتي لي
pump,
الجنتر
change
أول
the
امبارح.
excluding
قلت
factor
لك
of
أنا
another
بالدومز
pump. Each
بين
time you
أول
have to
امبارح
make the right click and you have to
وامبارح
say
كنت بالدومز
update
كمان.
processing method.
أنا بعرف حالي من ورا شغلي. أنا دقيت
So we'll do
لرفيقي
that
وقلت له
now.
إنه في
So
لاب
what
تحت
happens? So
طايف المي
basically you
وإذا فيك ما
apply
معروف
now
تشيل
that
الميات.
change
شو
to
عمل
all
هو؟
the samples and you
ضايق
saw
على
it
المكتب
went through
تبعولي
its integration settings
بطريقة
there,
إنه مثل تطبيق طناجر ما
right? It
هو
went through its
قصة
integration
كبيرة.
settings
المفروض
and
إنه
it
لازم تعرف.
reapplied those to all the samples.
إيمان قلت له
So
إن
now
الدكتور
the
قال لي إنه في
Terbutrem
مي تحت
is
لازم تشيل الميات قبل ما
and the Prometrim
يحفظ الدنيا.
is the
لا على المكتب
8.3.
بعتوا
I have to go
لي
to
حدا
another
يساعدني
sample
على مكتبي.
and see the
حدا
same
يساعد
thing is
مسؤولي
applied, right? Prometrim is there.
حدا
Okay, that's
يساعدني
correct.
في
We know
مي.
it. But when we
والله
just
إيمان
look,
النجار قالت لي إنه
over
في مي
here.
والدكتور دقيق لها.
Now Terbutrem.
هون دور راسه المعلمة مستر
We have
ميشيل
done
ملحم دور
that
راسه.
for all
مو بدي لمين لوكيلي.
through.
ما دقيت
Yeah, you
لوكيل هلا
see they're
سألته.
all the same, right?
قال لي
They all have that
إيمان
gray.
أنت
Talk about
يعني
that
قال لك كلمة
all
مستر
this
ميشيل
and
قال له
this.
إنه كيف هيدي البنت عندك الجنتر
So we have
الوكيل.
updated our integration
وأنت ما
parameters
بتعرف
and
إن
we
هي
have
أخذ رقم
applied
الدكتور
those
وبتتواصل
parameters
هي
now to
والدكتور ونحن أيمت
all
كنا ناخذ
samples
رقم
in this chart.
أرقام الدكاترة. المفروض إنه يكون في مي لازم الدكتور
There's
يتصل
one
على
more step
المكتب
that you have to take.
ونحن بنبعث له.
If
مش
you
هي
want
إيمان
to
بتتصرف
apply
من
this
عندها
to
من ورا
the
ظهرنا.
actual processing
عرفت
method
الطريقة كيف
for
وصلها؟
when you use it the
منه
next
تطبيق
time.
طناجر
And that is you
ومنه
have to
إنه
get
إيمان
processing method now
إنه حدا
out of the
يساعدني
results chart.
وصلها بهيدي الطريقة.
So this is a little tricky.
لقيتها وكيلي هلا قلت
You
له
want to write
معلم
this
هذه
in
السايد
your
أنا
notes.
بعرف شو عامل.
When you
قال لي إيمان
make
هيك
your results
وسعت
table,
الدنيا وقعدها مستوي مشان
you
علي إنه
actually get a
إنه أنت عاطي
copy of
رقمك
the
للدكتور. قلت
processing
له لا ما
method,
أنا آخذ
which
رقم
is now
للدكتور.
embedded
أوقات بيصير في مي
in the results
أوقات
table.
بيكون مصبطوه في
You don't see
الحنفية
it, but
أوقات
it's
بيكون في
أنا
شيء
بعتبرها
إنه نبعت وراي لأنه أنا بشتغل بالطوابة فوق. قال لي هيك ما اعتبرها لأنه الجنتر اللي قبل منك أنت اتصلتي فيه
And the reason for that is
قام هو
for data
وصلها
integrity.
للمكتب إنه
So
بطريقة
a
مثل
lot
ما هو
of
بده.
labs are,
قلت له ميرسي كثير
for
لإله
example, working in the
والله
pharmaceutical
يسامحه
industry
مش
and they
حقل لي
can't
شيء ما
change methods
حياته.
and so on. So we have this
ومستر
as
ميشيل بالنسبة
as
لمستر ميشيل
a,
هو ما بيحطني بالشغل
let's
أنا ما عندي
say,
مشكلة يمكن
feature
ساكت
in our software.
بس هذا اللي
So
صار.
if you make
إنه أنا
changes like we
غلطت
just did,
وتصرفت
and you
إنه
want
ما
to use
المفروض
that
إنه أنا
processing
أروح
method again,
برفيقي
then when you've
وأقول
made
له
all your
عرفت
changes,
كيف وصلها
you want to come up here to the process
ونق
method
خربوا لي الدنيا
pull down
كلها
menu.
ونقلني ما بين
You
أنا
want to come to
وفي.
save embedded method as.
هذا اللي صار.
And this
كبروها
gets
وعملوها ايدين ورجلين وما بعرف شو كيف برموه.
this
انه المفروض
gets
الدكتور يدق
out of the
المكتب
table
والمكتب نحن
embedded
بنبعث
method so
مش
that
والله
you
ايمان
can
بتروح
apply
تدق
it
للجنتر والجنتر.
and use it again. So
يعني
we'll
شو
just
بدي
go
لك
ahead and do
ما
that.
فيات
And then personally,
مفيات.
I'll go ahead and
بتمنى
overwrite
منك
this
انه هذا
one
الكلام هون لانه ما
because
بدي
these are the
يصير
correct
في
retention times out of this call.
يبعثوا لي على المكتب يجي يقولوا لي مش حكيت له
Don't want to
للدكتور
overwrite.
كيف هيدي المكتب
So
وانا
now when you go to
طمنت
make
انه
your
انا من هين
next
بشيء
chart,
الحمد لله
next result table, and you say
عارف انا
use,
شو الاسباب.
and you
مبسوطين مني
move
الكل
data
حتى
over,
كارولين تحت كلهم
now
مبسوطين مني
you
كلهم
come
دكاترة
here and
بالثالث.
use your processing method.
هي أول مرة
This
تجينا وحدة
processing
بتشيل
method
الدنيا
now
كلها من
has
هالطاولة بتنظف مع إني عنده مليون غرف أكثر من
you
عندك
don't
أكثر
do
من
those
عندك
two
بس ما تتخيل.
steps,
بس
you
أخذت
will
ريحتي
not
صرت
have
آخذ المفاتيح من كارولين وما في حدا يفوت الدكتور يتفاجأ.
that is a little bit tricky.
هذا اللي صار.
Just to
الحمد
make
لله على كل
sure
شيء.
that you
أنا الحق
do
علي
both
ما
of those
غلطت.
steps. I'll just go over those again because I see some
ضبطت لك انا المشكله.
questions coming in the
لا
chat.
أنت مخصك أنا اللي
All right,
غلطان.
so
قال لي مستر ميشيل كثير زعلان منك وكثير متضايق منك على التصرف اللي تصرفتيه وإيمت كلنا يا إيمان أنت عملت لي مشكلة لي أنا. قلت له قال لي أنا وكيل عليك يا إيمان أنت عملت لي مشكلة. ما قال لك أنا وكيل
So I
قال
did
لك
that.
وكيل أنا وكيل عليك.
Change
إنه
retention
أنت
time.
كيف
You just
إيمان
click and
بتاخذ رقم
drag.
الدكتور وأنت ما معك خبر. مع اللي أنت فوتيني بالحيطان لأني ما معي خبر يا إيمان.
Once I've made the change, I right click and I say update processing method
لا
for
مش هن دقوا لمشان ملحم مشان
This is
ملحم
the first
المعلم الكبير علينا
step.
وكيل على السيد.
I right click and I say update processing method.
قلت له بدي أعرف أنا شو
And I need to
الأسباب.
do that
هي أنا
for
غلطت
each
هي أنا عملت شيء.
individual change
يلا
that I
سامحنا
make.
ان شاء الله.
إن شاء الله أتمنى الخير.
And when I do that, I will apply the change
رامي كيف ننقيم
to all
هدول
the samples
الصور؟
that are in my result.
ما
صحي
بشوف
صباحي.
شو هن؟
صباحا كيف ننقيم. هدول هيدي السوداء اللي فوق.
سكوير اللي فوق.
هيدي
هاي السكوير اللي فوق.
ايه كيف ننقيم؟ من اللي عندنا من
So
سكرين هناك.
now I have applied
هيدي عادة
the change
بتبين
in all my
فيه ما
samples
في
to this
شيء مبين
result
هلا.
table.
لأن أمرار عم بيعمل
However,
سelection
there
بيطلع
is a
أسد
second
وبيطلع.
هلا بصير.
And the second step is to go back,
بس بدك تحكي لمستر الأشياء
export out of the chart
ما بتجيب السيرة ولا شيء.
the processing method with this new change.
يعني بترجع تبرم الخطرية بيرجعوا يبعتوا
embedded
وراي ساعتها بيطروني أنظار.
When
Every
time you make a chart, every time you make a results table, then
أنا كمان بدي
you
أعتذر
get
منك
a
كمان
copy of the processing method.
صعبت لك أي شيء إزعاج. أنا الحق
That
علي.
becomes the embedded
هو
method.
لازم المفروض
Do
أنا
not
لازم
affect
ما أقول إنه
original
أوعطي خبر
processing
إلي.
until you come to process method
اللي
and you say
ومجرد
save
للمكتب
embedded method
يساعدوني.
as. It's almost like export
بطريقة
the
إنه
embedded method.
كثير إيمان
And
جدا
now
كثير.
if
الدكتور
you
ده
do
إلى
this,
الإيمان
it
شوف
will
لوين
have the change
ضرني
that
مين
we
ضرني
made.
فيه.
And then we'll be able to use that processing method
عندي
again
أولاد وأنا عندي أولاد. عنده عيلة.
for other samples with the change. And there you see, there's our processing method. We made it. Actually, we made it yesterday.
من الخير.
So in this way, you can affect the processing method from the data within the results table. You don't have to go back to results new and then make a brand new processing method every time you have a change. And do it like this by this two-step process from within your data. I'll just hit cancel. We don't need to save it. Oops. That makes sense to everyone? So you only need to do this if you make some change. If everything is perfect and you don't make any changes, then you don't need to do that. But if you make a change, you have to go through that two-step process. The first step is to apply the change to all the samples in the result table. And the second step is to get the result, to get the processing method out of the result table to be able to use it again in the future with the change. Make sense?
Yes.
All right.
Yeah, I noticed that before you change the retention time for this particular sample, the Terbutrine flag for the library confidence was green check.
Yeah, you want to go back and see that? All right. So how do you do that? You highlight that. So yeah, I saw that too. So why is it green? So it's green because actually it did match the right compound. But you see it has the little asterisk there and it says smart confirmation. So actually it couldn't match Terbutrine because the match was so bad. But don't forget, in smart confirmation, we are matching by name first. So it looked for Terbutrine in the library and it tried to match it and it probably got horrible results. And so then it said, okay, that's not good enough. Then I will go and I will search the whole library anyway, and it found Prometrian, which is the right compound. This left peak is Prometrian, right? We've established that. And it's told you, okay, I've found a compound that matches with this score. However, I put the smart confirmation words there as a little asterisk to say, hey, it's not the same name as what you were looking for. So it's a match, but it's something different. So that's why we have a green check mark. Green check mark because the score is good. However, when we look at the hit, it's not the same name as what we want, which actually in this case is correct because Terbutrine is actually the second peak. Does that make sense?
Yes, perfect.
All right, great. So I think what we are going through here is a little bit tricky for sure, but it's really showing you that these green, yellow, and red marks are not yes or no. These green, yellow, and red marks are to help you, but you must look at the data and you must learn how to interpret it as well. And you are smarter than the green, yellow, and red marks, right? And of course, course, with experience, this will come. It's like learning a foreign language. You have to learn how to do all these things. It's not in one day you'll get it. But if you understand what's going on, don't put all of your confidence in these green, yellow, red marks at the beginning. All right. Did someone want to look at something in the library or?
Actually, Alec, we were not able to see what we did in this panel here because we have this bunker icon kind of hiding what we were actually doing there.
From this pull-down menu? Yeah.
Yeah.
So you have to go to Save Embedded Method As. That's a menu choice. I can't do it for some reason. Save Embedded Method As. That's all I'm doing, just selecting that choice from the process method. It says Save Embedded Method As. All right. Okay, so let's put it back over here. All right, so we have a couple things we got to talk about. Where shall we start? Shall we start with this no acquired MSMS business, or shall we look at the swath first? Well, the no acquired MSMS will be nice lead into the manual data. So in order to explore a little bit more about why this is happening and we have no acquired MSMS, that will be something nice to take us into the manual explore mode. So let's put that aside and let's go through the swath data first. And that'll also be a nice comparison with the IDA. And then what we'll do is we'll come back to this and we'll try to understand why we have a green, why we have a gray square here and no acquired MSMS for the IDA for this second compound. Okay, all right, so let's go to the swath. All right, so the swath, you don't see too much difference. And that's probably going to be true for most of the data that we have because these are very strong, nice, clean peaks. So the MSMS is not affected. Right here we have a really excellent fit and purity 100 score, and also for atrazine. Okay, so the purities start to drop a little bit, and you can see that. So there, so does anybody see any extra peaks? Yes, there is a 176. There's a 218. Does anybody know what those are? What is different? So we didn't see that in Ametrian, right? Look in Ametrian. Ametrian, we didn't see really any extra peaks. There's just a few right there. But when we go to atrazine, now you see the purity score did drop and reverse fit did drop. Fit is still excellent, right? We know that's the case because the fit score is based upon every peak in the library having its match in the data, which it does. If you look closely, right, every peak in the library has a match in the data. But we have these extra peaks in the data, right? 176, 218. So they're there. But what is that? Can someone tell me, please, what is the 176? What is the 218? And I would encourage you to answer the question to look at the difference in the formula between ametrine and atrazine. There's something very interesting in the difference in the formula, which is actually leading to this difference in the data. Anyone have any ideas? 2 hydrogen, somebody wrote. Okay, so could be 2 hydrogen, but we don't have a 2 hydrogen difference in the formula, right? In the formula we have a 3 hydrogen difference, H14 to H17.
Sorry, Alek.
Yes?
Sorry, Alek, can you please repeat the question? I didn't get it the first time.
All right.
Sorry.
So the question is, so Ametrian has a nice match. As you see, we have perfect fit, reverse fit impurity. And you can see that every peak in the library has a match and vice versa. There's not a lot of extra data. And that makes sense because this peak is very strong and it kind of stands alone. So it's going to be the primary parent in the swath window. So for Ametrian, we didn't see a lot of difference with the IDA data. Now we go to atrazine. Atrazine also is green. We have a nice peak. It's not quite as strong as the Ametrian. And then I started to focus on the MSMS data. And I saw, okay, my purity is a little bit less. And that is expected. Because this is swath data, there will be other parents in the swath window which will contribute some other daughter ions. And those daughter ions will be in the data, and then they won't match the library. So then I started to look, okay, I wanted to show you an example. Where is an example of a daughter ion that's in the data that's not in the library? And I saw two, right? 176 and 218. And then I saw other ones, for example, right here, right here, right here. And so then I proposed the question to you, okay, there's something unique about these extra daughter ions. We actually know what they are. So I want to know, the question is, where does the 176 and the 218, for example, come from? And in order to answer the question, you need to look closely at the formula difference between Ametrian and atrazine. There is something standing out there as a formula difference. Someone in the chat, they wrote 2 hydrogens, which, yeah, it's a good guess, but not exactly correct. 2 hydrogens kind of makes sense because it's 2 difference, right? But we don't have a 2 difference in the formula. We don't have 2 hydrogen difference in the formula. So I heard somebody say,
Chlorine.
yes,
The Cl is isotope, so 35 and 37.
correct, exactly correct. So atrazine, so I will go through why. So that is the correct answer. So atrazine has a chlorine and Ametrian doesn't. And we spent a lot of time on the first day talking about isotopes, and we talked about these special elements that have a very strong isotope. And chlorine is one of them. As the gentleman said, right, we have chlorine 35 and we have chlorine 37, and they, I think I remember something like 75-25%, right, relative intensity. So what's happening in the swath is not selecting just the parent, the swath is selecting all of the isotope pattern as well, because the swath window is much wider. So here, you notice I didn't talk about the middle pane, right? That was a little sneaky of me, yeah, because the answer also comes from the middle pane. Here is the MS spectrum. The swath is not selecting just the 216. Here's the isotope of chlorine at 218. So we are actually doing MSMS on all of this together. All of it goes through the swath window. So these extra peaks, in this specific case of having a chlorine isotope, we know where they come from. They come from the chlorine isotope of the same compound. And I believe in the lecture there was even one slide on that. When I showed you the swath MSMS spectrum, we pointed out that those extra peaks in that picture were also coming from the isotope. So that's the main difference here between Ametrian and atrazine, and also between the swath and the IDA. Just to verify that, let's go back to the IDA data and we'll look at atrazine. Okay, so let's just choose one of these. Here we go. And we'll look at atrazine. You see those peaks are missing. All the other data looks exactly the same. We have the same XIC, we have the same mass spectrum with the same isotope pattern because the MS is actually the same. What's different is the selection of the MSMS. In IDA, we are just selecting a 1 Dalton region around this parent, 216. So we are not selecting the 218 for MSMS. So I mentioned the words like clean MSMS and dirty MSMS. That's not an official term, okay, but I like to think of it like that. The IDA is clean MSMS because it selects just one parent with one Dalton wide window, whereas the SWAF, here's the SWAF, right? There's atrazine in the SWAF. The SWAF, all of this is being selected in the window. Now, I don't remember exactly how we set it up. We have to go back and look, but I can't remember if I did this.
الو
All of those.
اهلا جود مورنينج، كيف حالك؟ اهلا كمان، كيف حالك؟ ان شاء الله بخير. اي رقم؟ انا معي هذا، انا اللي بعته لكن الورك اوردر. ايه اورايت، بيكون الورك اوردر يمكن ما هيك كان عندكم بكثير. ايه هو انا هذا انا الريكوزيشن نمبر اللي انا حاطه من الاساس. ايه طيب اورايت اوكي ثانك يو.
Central Zone.
الو استاذ علي بلوط، كيف حالك؟ كيف حالك؟ شو الاخبار؟ لا ولا همك. ايه ايه تفضل. ايه امم امم ايه اكيد اكيد صح. ايه ايه امم لا خلينا نوصله خلينا نوصله ونضل فوق راسه وقت يجي يشتغل انه يعمل بالطريقه مضبوطه. ماشي سلم هالدقيقة، يعطيك الف. لا بالعكس اهلا ولا يهمك. شكرا لك.
So that would be some math perhaps I would find that validate together would be to take the same samples. You don't have to take all. Let's take one spike in a lower concentration whatever concentration.
بونجور سليم، كيف حالك؟ تمام؟ يعطيك شكلك بميتينج. أنا بدي أسألك سؤال. هلا أنا بعت لك الريكوزيشن نمبر اللي نحن بعتينا بالأول للفيزيكال بلانت. ايه هو الآن بيرجع هن they issue another one من عندهم، ما هي؟ وبدي اسألك هيدا قيمته بتكون أقل من ما they quoted us صح؟
Okay, so any questions on SWOT versus IDA function? Sorry, different language, what is the difference?
خالصة يعني.
Good example,
قد إيه قيمته هيدا دخلك؟ 2500. 2500. اوكي، يمكن لان هن بيخلوا شيء لغير شيء، ما هي يعني انا الريكوست اللي بعت لهم اياها قيمتها 3410. امم هن بيرجعوا بقسموها. ايه طيب خير ماشي. alright thank you. باي باي.
There's the big difference for us now. We have the gray icon here for terbutrin, not chosen for MSMS in this IDA data, but in the SWOF data, it doesn't need to be chosen. There's MSMS of everything, every cycle. So we have the green check mark there. All right, so any questions on IDA versus SWOF?
No, thank you, Alek. All is clear.
Everything's good? All right. Okay, so what we'll do now is we'll go back to the IDA data and we'll try to investigate why exactly we have that green icon. So we know what happened, right? It was not chosen for MSMS. However, we want to try to understand why it was not chosen. So we'll go through that now. We'll go back to our actual acquisition method. And we'll take a look at the acquisition method, and we'll start to look in the acquisition method. What were our IDA settings? And I went through that quite quickly when we set the methods up. So I'll talk about that in more detail. And then we'll come back to the data and we'll see, okay, again, we have the gray square, and then we'll go into the manual data and we'll try to look and see in the manual data if we can learn more about why that gray square is there. And then that will also be a nice introduction for you to the manual data analysis. All right, so let's go to analyst. Oh, sorry. I'm doing too many things on too many different days. We don't have analyst here. Analyst is our old software. Apologies. We have the methods are inside SCIEX. One day I'm doing one thing, the next day I'm doing the other, and I get confused. Apologies for that. So here's the MS method, and here's the IDA method. And here we go. So this is our IDA method. This was the method we used to collect the IDA data. And what we're going to talk about now is the settings in the blue box. So this is the IDA criteria. Would it be helpful if we just went back to the training presentation briefly, and I just showed you exactly what I'm talking about from the slides in the training presentation? I think that would be helpful. Where was that? We put it on the V drive, I think, right? Does anyone remember how we opened that? We put it in downloads. Oh, here it is. Okay, so I'll get it out of downloads and I'll put it on the V drive. So everything is on the V drive. I really don't like to keep things on the C drive. Okay. It went on the other window. Can somebody help me out and please bring it onto this window?
Okay, Yara, 1 second.
Okay, thank you. Yes, it's coming. All right, great, thank you. Okay, so we don't have any security risks and we don't need this thing. All right, so let me just find the IDA slide. Yes, I saw it. All right, so you remember this slide. Okay, so just a brief review of what IDA is doing, right? We have a survey scan, and the survey scan is looking into the data in real time and seeing what's present. And when the survey scan identifies something, it sends it to the dependent scan, and the dependent scan does MSMS. You cannot see. Yes, we lost the red, so I have to share. And I think that actually stopped sharing. Now I have to go here. Oh, that stops the sharing, and then I have to go here, and I have to choose, I guess, screen 1, yes. Okay, now can you see?
Yes, we do.
Okay, great, sorry about that. Okay, so here is the slide from the training that the lecture part we had in the training, and we're just gonna briefly review what is IDA doing, okay? I know we're going over this a couple times, but it doesn't hurt. So in IDA, we have a survey scan. The survey scan is looking into the data, and it's seeing what is present, every scan. And it identifies some things that look nice for MSMS, and it sends them to do MSMS, and that's called the dependent scan. So the survey is the top MS scan, and the dependent is the MSMS. And don't forget, in MSMS, we have to know what we want to do MSMS on. In IDA, we are choosing single parents. What are we going to do MSMS on? Before the sample, we don't know. So we need this IDA to help us choose what to do MSMS on. And we have this threshold. And this threshold is the control of what goes from the survey to the dependent. So we're going to talk about the threshold. And the threshold is everything inside the OS, everything in this blue box. So here's the survey scan, that's the top MS. Here's the MSMS, that's the dependent scan. And this is the threshold. It's called here IDA criteria, and actually threshold is only one part of that. But we need to understand all the parts. All right, so the first thing is pretty easy. Every cycle we're going to choose 10 parents to do MSMS on. And you can adjust that, of course, up or down. But don't forget that each scan that you then do requires time, right? So here we have 70 milliseconds for 1. So 10 is going to take approximately 700 milliseconds, right? So if you put here 20, okay, you might think that's good, right? Because you're going to do MSMS of more things. And don't forget, we're trying to investigate why we have that gray mark in the data, right? The gray mark is because that compound was not chosen. So maybe doing more MSMS is a possible solution. However, when we do that, look what happens. Now our scan time went up to almost 1.6 seconds. So we lost half of our data points. And already you heard me complain this morning about, oh, the peaks look a little bit too much like triangles, right? Not enough data points. So actually, for good data quality, we should be going the other way. We should be either reducing our time or reducing our number of scans. So that's one possibility to change, but perhaps not realistic to change at this point. Intensity threshold, well, I think that'll come into play more next week when you investigate the different concentrations. Right now, everything is quite high concentration, right? Let's just go and take a look. So you see here, these are in the E5s. And when we look at the mass spectrum, here we are in the E4s. So 50 is teeny tiny, right? Very small. So we're not really worried about the threshold at this point. But when you come in next week with 100 times less, you may want to think about your threshold in terms of, 50 is quite small. Is 100 times less going to be a little bit taller or a little bit shorter than 50? Looks to me when we zoom in that our background chemical noise is sitting right around 200, right? So probably anyway we could raise that, because below 200 it's going to be very difficult to find anything. Because this part, you see this part, this is the chemical, just background chemical and electrical noise. And if we zoom into another part of the spectrum, probably see the same thing. Yeah, you see that? So this is no, that's a real signal, right? That's a real signal, but this here is not real. So about 200 is probably an appropriate threshold. So 50 might even be a little bit too low. But that's certainly not impacting why we have this gray mark, because anyway, here is terbutrin way up here at 15,000, right? So that's E4's level. So we could adjust that a little bit higher, up to maybe 200. That's probably not a bad thing to do, but that's not going to affect why we have the gray mark. All right, so let's look at the next setting that we chose, which is here, which is called exclude former candidate ions. So what this means is, if we do MSMS on one parent for a couple cycles, then maybe we don't need to do MSMS on it again. Getting multiple MSMS from the same thing is not really useful. Once we have at least one good quality MSMS from a parent, let's move on, right? Let's do MSMS on another parent. That will increase the richness of our data files and give us more data that we can use. Having 10 MSMS on the same parent is not going to give us any more information than one. It's just a little bit of waste. So that's why we set this up. And we said, okay, do MSMS 3 times, after 3 times, and then you'll forget about it for 12 seconds. So let's go to Paint, and I'll draw what happens. So we have here chromatogram, so T for time, I for intensity, right? And then we have our data, right? And then here's the peak, all right? And then we have a situation like this, right? One is chromatrin and one is terbutrin. All right, and I'll draw the data points. So you probably already understand that this is the setting that's going to impact us, right? Because what did we tell it to do? We told it to do only 3 MSMS and then forget about it. So where are we going to get MSMS? Probably we're not going to get MSMS on those 2 because they're below the threshold. Then we'll get MSMS here, and we'll get MSMS here, and we'll get MSMS here, and then what happens? No MSMS for 12 seconds, right? And how wide are our peaks? Our peaks are only 8 seconds wide. 12 seconds. So this is the setting which is impacting why we have that gray X. The software doesn't know that these are 2 different compounds. It's looking into the MS information. In terms of the MS information, terbutrin and chromatrin are the same, right? They are just isomers, so they have the same formula, they have the same mass. They're not different, this data. They are only different in the MSMS data itself. So we set this up perhaps a little bit incorrectly to look at isomer analysis. So we could do a couple things. We could do, we could say, okay, do more MSMS. So do maybe 6 or 7 MSMS and then forget about it. We might turn this setting off altogether. which is perhaps not a bad idea because anyway, we don't have so many data points. So each peak is only 4, 5, 6 data points. So perhaps we can turn it off and run again, and then we'll get MSMS hopefully. So these data points will be perhaps below the threshold because the threshold is actually looking at a rate of change. So these will be negative. This one will not because it's still above that one. This one probably will be negative. This will be negative because the intensity is going down. And we'll get MSMS also here and maybe here. And then we won't get it on the way down. That would be the plan anyway. So if we turn it off, we're probably not going to lose so much because our peaks are quite narrow anyway. We have quite good chromatography. So I think this is the reason why we have the gray mark. And what we'll do now is, well, first I'll open it up for questions. But what we'll do next is we'll go into the data and we'll manually explore how much MSMS we actually got. And that'll be something that interesting that we can do as part of the method development, really. But this is also important in your in your data analysis. If you do want to go and look at isomers and so on, you will need to know how to change between MSMS spectra. So does this make sense to everybody?
Yes, Alek.
Okay, great. All right, so obviously to turn it off, just uncheck it, right? Goes away. Check it, you can say, okay, after 8 times or something. Oh, not maybe 8 times. Or we could reduce the amount of seconds to forget. So this is definitely a setting that you can play with yourself. All right, so let's go back to the data. So here's the data in analytics. Now, there's 2 ways you could approach this to go to explore mode. You can go to explore mode from the home page. You can say home, and you can say, okay, explore, and then you have to come to open. And we have to find then the individual data file in order to open it. There is a shortcut button from the analytics. All right, so Samar is here. Okay, so we have to, there is a shortcut button from analytics, and that is this button right here. And personally, I make use of this button a lot because I may be working on something in analytics and then I want to take exactly the screen I have and bring it to explore. That can be quite useful. If you click on that, then you see we go to explore mode, and it opens the data file exactly what we were looking at. So explore mode works one on top of the other. So you have vertical, whereas in analytics, it's kind of horizontal across. So this is the XIC, that'll be on top. This is the MS, that'll be in the middle, and the MSMS, if there was MSMS, would be on the bottom. So here's the XIC, and here's the MSMS spectrum from the XIC at that time. So it's just kind of flipped. And you were asking before, I think somebody asked this before, how can I see more of the mass spectrum? How can I see more of the chromatogram? Well, you have to come to explore to do that. So here you can double click now on the axis and you see you have the whole chromatogram shown to you. And you can double click on this axis and now you have the whole mass spectrum shown to you. And this is much more powerful to go and to look at other things, whereas in analytics, right, you just have this zoom. We can go out in terms of the chromatogram, but not in terms of the mass spectrum, right? It's impossible to zoom out. So if you do want to see other things, then you can come here to the mass spectrum. Now, at the moment, we don't have any control over where this MSMS is. Do you remember when we talked about the data in the lecture, I said, for example, that you can double click in a chromatogram. So if I double click in a chromatogram, I get the mass spectrum at that point. And you see now that this gray line appeared. And now I can use the arrow. You see the arrow, the cursor turns into a double-headed arrow. And I can now drag that line to wherever I want, and I can see the mass spectrum exactly at that place. So I can move it around. Unfortunately, this one, when you open it from analytics, it doesn't have that gray line. So this one, we cannot move it. So actually, I will delete it. But what we can do is we can put this one, whoops, it's hard for me to do over the internet connection. There we go. We can put this one right here. Right? And then we can see, okay, this is the mass spectrum at that time. Now, this is really our first look at the raw data. And you kind of see, you kind of get a feel now of actually how powerful this instrument is. The mass we're looking at is 242.143. Do you see it here? So I zoomed out, right? Where is 242? 242 is right here. So there it is, 242. So that's the parent we're looking at. And you can see there are all of these other parents present in the mass spectrum. And this is, I would say, a pretty clean mass spectrum even. So everything in terms of cleanliness and so on is okay, but electrospray is just such a dirty process. You have all of these other items. Now these, of course, also may be compounds present in your sample. We don't know that right now. But this is normal. This is very normal to see that your parent of interest is right here, buried in all of these other parents. Okay, so what can we do first of all? Maybe we just have a little bit of navigation around the Explore mode, and then we'll go, and then that'll lead us, I think, into something called the IDA Explorer. And then we'll go back to answering our initial question, which is still, why do we have that green, and why do we have that gray square? So any questions on this point from here? All right. So when you use this button to come from analytics to explore mode, like I said, you have only these panes. If you want to see a little bit more about the sample, for example, if you want to see the TIC, you can come to show, and then you can say TIC, total ion chromatogram, and you will get a box that asks you which experiment you want to see. Now, if you leave it on the top, then you will get a TIC, I think, for all the experiments. Let me just check that. No, it just gives you, yes, it does. This is a TIC for all of the experiments overlaid. And I can see that because I know there's this double-headed arrow here. See that? This double-headed arrow. And this double-headed arrow, if you double-click it, now will give you the TIC for each of the experiments. Or you can say, show the TIC, and then you can choose the sub-experiment you want. So we have 11 experiments. Why do we have 11 experiments? Well, think back to how we made the method. We have the one time-of-flight scan, and then we asked for 10 IDA MSMS. So 1 plus 10 is 11. And you can see that it's here. The first one is the top MS, and then 2 through 11 are all of the IDA MSMS. So shortcut, you can jump to the one you want, or you can select them all by clicking here on period 1, and then you will get one massive TIC, which has this double-headed arrow. And hang on just 1 second, please. Hang on 1 second. Sorry, I thought I heard a strange noise. Okay. So in order to see now the individual TICs, I can double click this arrow. And now you will see they have expanded out with all different colors. And the color code is over here on the left side. And we have the blue for the TOF IDA. And we have all the other colors for the IDA TOF MSMS. Experiments 2 through 11. And if I just zoom in here and show you all of the colors down below, so there they are. So the MSMS has lower intensity than the MS. And this is the window that will open when you open a data file as well, this full TIC. So you have to know how to get out the data you want. You have one pane which is active, and that is the trace that you click on. You see that it's bold. And then what you can do is you can right-click, and you have some options. You can say, remove the active trace. It will delete only the active trace, or it will remove all the traces except the active trace. So that will get rid of 2 through 11. So if I do that, now I'm left with the TIC of just the MS experiment. So that again shows you really how powerful the time of flight is. This is the TIC of all of the ions that the instrument saw at every scan in terms of the MS. This is the XIC at the top for 242.143, which is the exact mass of the terbutrin and the chromatrin. So you can see we don't even see that peak present in the TIC, and this is pretty normal. In order for something to be a peak in the TIC, it really has to be very strong. So this is why either making these XICs manually or using the analytics to do it for you is so powerful. Because it will be very difficult to go through the data manually and to try to find what are the masses. So we're done with this one. Let me delete this one. We can delete the panes by pressing the trash. There are also these series of buttons here. These 3 buttons hide different panes. So the active pane has a gold box around it. And the first button hides this pane. So if I click that, it will just hide it. It's not actually deleted, it's hidden. And then the button here says show all the hidden panes. So I can bring it back. And then this other button in the middle, it hides all the other panes. So those are very useful 3 buttons to zoom in and out by panes when you're working with a complex data set. So we have those 3. So we have those 3 buttons which hide and show the different panes. We have the garbage can, deletes the pane, and then the 2 garbage cans deletes all the other panes. So those buttons there are help you to navigate through your panes. If you want to move a pane around, you can use the truck. So we can click and drag on the truck, and then where you put the click and drag, you see I now have a red line there. So I will move that pane up to where the red line is. And I can also put the panes next to each other. So now I have them next to each other. So I'm just clicking and dragging from the truck, and then I'm releasing at the red line. So that's kind of the navigation around the software, how to move the panes, and how to zoom in and zoom out, and so on. So I think what we'll do now is we'll talk in depth about the XIC. So I'm going to get rid of the MSMS. I will delete it. and I will put my TIC on the top and my XIC below. All right, so the TIC, don't forget we opened that by opening the data file and going to show, and then show TIC. This XIC is still the XIC that came from analytics, and you can see it says that afterwards, right, from analytics. Okay, so do you remember also when we were setting up the processing method, we talked about this XIC width. So the TIC, the top one, basically has the width of the whole mass spectrum. Right? This is the sum of all of the ions at each time point. So if I just double click somewhere, right, this is the mass spectrum at that point. Where does this intensity come from? That point right there. That intensity comes from the sum of all of these ions. All of this added up, all of this intensity added up equals that intensity, E6. So you can think of the TIC as having the width of the whole mass spectrum, 200 to 1600, exactly what we chose. Now the XIC basically has a much narrower width, and that width is focused on the compound we want. And you see by doing that, of course, the background drops away. So this is an XIC of 242.143, which is the exact mass of chromatrin terbutrin, plus or minus 0.01. And then we get this picture. So by using the high resolution and by narrowing down the width of the XIC, we get these very clear chromatographs. So what I'm going to do now is I'm going to demonstrate that to you by making a bunch of XICs with different width. So I will come to show XIC, and I will replace this with 242.143. Why can't I type? Come on. 24143, 242.143, 242.143, 242.143. Okay, so we'll do a width of something like 0.7. And then we'll do 0.1, and then we'll do 0.05, 0.01, or no, 0.02, 0.01. And then I'll get rid of this. So what we're going to do is we're going to pull out 5 XICs. They all have the same center, which is exactly chromatin terbutrin, but they have different widths. So I'll go ahead and do that. And here you see we get now all of the TICs here. And I'll just zoom in. I will move my mass spectrum to what is, it's hard to do with me. Okay, so what is the retention time? 8.319. So that should be right here. And we have 242. There it is. So there's our mass. And we are lucky that the background is so low. So maybe there will not be so much difference. I'll just hide this one at the bottom. Okay, so here are the 4 XICs, and actually I was hoping for a little bit more difference than that, but it doesn't seem that there is. Okay, I'll just zoom in. So the dark blue is the biggest width, and that is of 0.7. And then pink is the next with 0.05, and then oh, sorry, that was 0.1, because here it's confusing. Sorry, here it's saying plus and minus, but in the box we just did width. So you have to double this to get the width. So that was 0.7, this is 0.1, this is 0.05, this is 0.02, and this is 0.01. So what it is doing is it is taking all of the intensity. Let's do the 0.7 first. Here's the center, right? 242.143, 242.143. And it is going from let's say minus 0.3 to plus 0.3. So it's starting somewhere like right here, all the way to right here. Right? So all of the intensity inside that box is plotted over time to make the blue trace. And the pink trace is more narrow, like this. Right? And as it goes, I made it more and more and more narrow. And you see eventually the intensity starts dropping off. I'll zoom in here. Probably because the last one is actually taking only this part of the peak. So that's what it means by XIC width. How wide a range of the mass spectrum are you actually looking at when you produce the selected ion chromatogram? And of course, we can get away with using plus or minus 0.01 because we have such high resolution on this instrument, and that'll give us high specificity. The example is not so great because the background is really clean. There are no other peaks close by. But perhaps in a dirtier sample, you would see a bigger difference. And the first one, the dark blue one with the width of 0.7, would be very messy because other masses would be included in it. So that would not make sense to use it. So that's why we can get away, not get away, that's why we prefer to use an XIC width of 0.02. So this one, the green one, is the one that is used in the analytics. Plus or minus 0.01 times 2 is a width of 0.02. Does everybody remember where that setting is? Just refresh your memory. So in analytics, we just go to look at the method, and under components, right, we didn't touch it, but it's here, XIC width. That setting there, XIC width, you can type whatever you want, right? So if you wanted to do 0.7, you're free to do that. But that setting there is controlling the width that the software is using to produce the XIC from the full scan data. So in a sense, you control here the resolution and the specificity of your selected ion chromatograms by adjusting this width. Does that make sense to everyone? All right, I'll take that as a yes. What I would like to do at this point, before we go a little bit further, is to just take 5 minutes break, if that's okay. I'll refill my water glass, and then we'll continue in the explore mode to look around a little bit more, in the data. And we'll start to look now. We didn't look at this point yet at the MSMS part of the data. We just focused on the mass, and we focused on the XICs. So we still didn't even start to answer why we have that gray square and why we are missing MSMS for the second peak here. I mean, we kind of know why, because we set up that setting in the method to forget about the compound after 3 MSMS. But we need to go into the data and prove that. All right, so compose yourselves for 5 minutes, and we will meet back here again. Now it's 10:58, so we'll meet back at 11:03. All right? Okay, so talk to you guys in 5 minutes. Very nice tutorial. It's here under the Start menu. The SCIEX? Oh, maybe SCIEX OS. Excuse me, so yeah, SCIEX OS documentation. And then you have here OS Explorer tutorial. The other stuff, I would say the other stuff is not really very useful. to be honest, but this is really excellent. So this is a very nice tutorial, and it comes from the fact that this part of the software is actually quite old. So we've had it for a long time. And it goes through basically step by step everything that I'm explaining to you. And there are some data files which you will find in your SCIEX OS. So I don't know if you have the DVD or not, or the zip file that you downloaded from the internet. Maybe if we are lucky, the service engineer left that on the V drive software. Yeah, here's SCIEX OS 2, and then you have well, why don't I read it? Where does it say? In the folder extras example project. Did they leave it out in the? Zip drivers install. All right, well, I can send those to you if you don't find it. It's not going to be under firmware updater, and it's not going to be under drivers, I'm pretty sure. And that's lame. Looks like in version 2 they took it out. Okay, well, I can send you these. Data files. Let me make a note to do that, and then you have the data files, and you can go through step by step in the tutorial here, and it's really, it talks about the panes, it talks about the buttons I talked about. It probably actually goes into more detail even than me. So yeah, you see it explains about the truck, how to move the panes. So this is really a very valuable document. I wish all of our guides were so nice. So it really covers everything. So if you like, what I will do is I will save a copy also in my folder that I set up for you on the V drive, and have a copy there as well. All right, so don't worry if you didn't get every exact note about the things that I'm talking about. Okay, so I have to send AUV example project files. Yeah, it doesn't install an example project, right? I didn't see example here. Yeah, weird. Default, no example project. All right. I'll send you those files, and then you can, I'll do it now. I'll create an example. Thinking. All right. So now you have example project there, and then I'll send you the data files. You can copy it into that project. Just close these so it stops complaining. Okay. All right. So we talked about how to make an XIC. We talked about XIC width. One other trick that you can do is you can come to show, you can come to XIC, and you don't need to type a mass here. You can type, for example, a formula. So if you just know the formula, for example, you can put that. And then it will produce, you see here the last one, it produces the mass for you. So you don't need to, if you don't know the mass exactly, you might find it easier to just type the formula directly into the XIC box. You know, to search for the different triazines, what you could do is go to show XIC and put all the formulas there. So let's do that together now. We have the DVD for 1.7. Maybe it is there. Yeah, okay, that's cool. You could check on there and then let me know. It was in Excel, I think, right? Triazines. Here we go. So here's the formulas. So we can just do the formulas right into the Explorer. And of course, make the widths correct. And then when you do that, it puts the formula over in the compound name too. So then we can say, okay, so now we have, and this is nice for papers and stuff, you have a colored line for each one of the pesticides overlapped in one picture. And you can minimize that like that, right? So there's all the triazine pesticides, what we analyzed in one overlaid multi-XIC picture. So that's something else you can do in Explorer. Okay, so I think we talked about everything to do with MS data from the Explorer. We know how to look at a peak, and we know how to produce an XIC, and we know how to look at the mass spectrum. One more thing, from a mass spectrum itself, so let's say here's a mass spectrum. If I want to produce an XIC directly from the mass spectrum, I can highlight the peak that I want to see over time, draw a little blue box around it like that, and then I can double click that box. Now it'll give you a message. I suggest whenever these kind of messages come up in our software that you never hide them. You can check this box and then you will never see it again. However, you guys have so many users and so on, it's better not to do that. So the message comes every time. It may be annoying to some of you, but it's then going to tell everybody what's going on. So what happens when you do that is about the width of the XIC. It is not using a specific width this way. It is taking the width of the peak at half the height. So what that means is, I'll say cancel. What that means is, this is the peak I selected. It jumps to that peak. It finds the mass, and then it comes down to half the height, and it's using this XIC width. So it's just giving you a warning that if you do this way of producing XICs from slightly different data, you may get slightly different XICs because that width may be slightly different from data to data. So it is not a fixed width like in analytics or like in when we go to show XIC. So that's what that message is telling you. It's telling you it's going to automatically determine the width based upon the width at half the height of the peak that it identified. So we say, okay, and then you see we get an XIC. There's the XIC for that mass that appeared. So basically a rule of thumb is if you double click in a chromatogram, you'll get a mass spectrum. If you select in a mass spectrum and double click, you'll get a chromatogram. it'll be a selected ion chromatogram, but it'll be a chromatogram. And that continues forever. This is full scan data, so you can go through the data forever. Double-clicking in a chromatogram always gives you the mass spectrum at that point. And then selecting and double-clicking in a spectrum gives you the chromatogram of that. So this goes back to the fact that the data is three-dimensional. And it's very hard to show it in one picture. So you're always seeing two dimensions, and you double-click to get the third dimension. That makes sense to everybody? Just going to have to come and practice, right, a little bit too, so you all get familiar. And don't forget, it's all in the tutorial. Okay, so now let's look at some MSMS data. So in order to do that, did I hide any panes? Yes, I had some panes hidden. Okay, so I will go back to, I'll go back to what we started with. Shall we do it that way? Is it the best way? Yeah. Yeah, let's even close this and go back to analytics and press this button again. So we're back in analytics, we have that gray mark, and we want to know why there's no MSMS over here. We'll push that button. Now we're in Explore, and the two pieces of data that we have,
ماشي مهم بس
here's
هيك ما
the XIC, and here is the MS. Now, you may think, okay, we can go to show, and we can go to, show, and we can go to TIC, and then here we have all of the MSMS chromatograms. But that's a little bit tricky because they are individual chromatograms from the 10 different MSMS experiments. So how are we going to know the MSMS of the parents is in which experiment? We have to look in each of the experiments and try to find it. It would be a little bit like looking for a needle in a haystack. So we have another way specifically to look at IDA data, and that is called the IDA Explorer. You see that here. Show IDA Explorer. So I'm going to click on that, and the IDA Explorer opens. So what we have here, we'll talk about the left side first. So this is the IDA Explorer, this middle pane. What we have here on the left side is a dot plot. And each dot represents one MSMS activity, one MSMS scan. The x-axis is time, and the y-axis is the mass per charge of the parent. And when you click on the dot, I click on that dot, then over here on the right side I have the MSMS of that dot, that parent. So you can see how many MSMS the system is actually doing, quite a lot, right? It's choosing many, many, many MSMS. So every cycle, we get 10 MSMS. So now what we need to do, it's actually quite easy. What we need to do is we need to go into the data using the IDA Explorer and find out what happened to chromitrin terbutrin. So we need to know a couple things first. We need to know approximate retention time, and we need to know parent mass. So both of those, it's very easy to know, right? We can read it right from the XIC. Here's the parent mass, 242.143. That's the parent mass of chromobutyrin and terbutarin. And the retention time is here, right? 8.3, 8.4. So what we're going to do, we're going to go and we're going to look at the data at that point, and we're going to try to determine what the instrument was doing and why it didn't choose the second peak for MSMS. So parent, I'm going to zoom in. So down here somewhere, right? 242. Okay, this can be a lot easier if I hide this bottom pane. I will hide this one, hide the pane. Okay. So here's 242. Here's between 240 and 250. And we are looking retention time about 8.3, so I will zoom in 8 minutes. All right, so now you see each dot, once you zoom in, is labeled with its parent mass and a slash and the retention time. So we can see, okay, where is 243? It's right here, right? 242.143 is right here. And when I click on that, I have the MSMS over here, and we looked at this now a couple times, right? So this is familiar to us. Yes, the 200 and the 158. If you would like to see the survey scan and the XIC as well, you have buttons to do that. Here is to show the XIC. So now that picture looks identical to this picture because it is the same, right? It's the same parent mass. This XIC just came from analytics, and this one came from the IDA Explorer. But the nice thing is by pushing this button, they are linked. And now you see a blue dot. So the blue dot is the time point that we are at on the dot that we clicked on the IDA Explorer. So this is the XIC, and then we can also show the survey scan. Right here, show the survey spectrum. And so now we have the survey spectrum. I'm going to use the truck to organize a little bit better. So now I have my 4 panes. I have the IDA Explorer. Here I have the MSMS. And if you get confused, just read it right from the top, right? Here it says IDA, TOF, MSMS. Here it says IDA, TOF, MS. Here it's, okay, you have to look at the x-axis and see that that's a time, and then you see it's a chromatogram of the TOF MS, and there's the mass with the width. So what we are trying to establish is why we didn't get any MSMS further across this peak. So there's one, and there's the second MSMS, and then there's the third MSMS. So actually we did that quite nicely because we have it right at the top, right? That's perfect. But then there's no more. Why is there no more? Because we told it to forget about it. So it's clear we have 3 MSMS up the side of this peak. That's exactly the drawing I drew in paint, right? And then we forgot about it, and we didn't do MSMS on these other data points down here. So we have no MSMS of the second peak. So it's clear now the instrument is doing exactly what we told it to do. Do MSMS 3 times, and then forget about this and go and find something else to do MSMS on. So is that clear to everyone how to use the IDA Explorer? So anytime you need to see, okay, I want to see if there's MSMS of a certain parent or a certain daughter, you can come to the Explorer and you can zoom in and you can find it, and then you click on the dot, and then all 4 datas update. See that? All 4 datas update, and there's your XIC with the dot, and you have the survey scan, and you have the MSMS.
Excuse me, I have a question. The export data for this for this combination of 6 graphs can be done individually and all of them? How can it?
So there's not, unfortunately, there's
As
not
a report or something.
Yeah, so unfortunately from the Explore mode, there is not really a great way to get a report because it's meant to be manual data analysis. So I would suggest, unfortunately, that the best way is a screen grab. Because a screen grab, you can get, right, yes. You do have print, and you can print the window, or you can print the pane. Okay, let's try it, PDF. Let's try to turn it on its side so we do, it is already landscape, okay.
Yeah, but printing it does not give you the data for publication, scientific publications.
Yes.
It's better to put them a different export like an Excel or CFR. Yeah, exactly, so that you can adjust the data and the XY, the X-axis and the Y-axis for better draw.
Exactly. So you have all the data here in a table format. Of the IDA, and also each one of the graphs you can say, yes, how do I? But this is. Then you're going to have a huge number of somewhere there is. Here data and peaks table. So this is actually the data then that makes this trace, and you have each time point. With
you can export it or you copy paste it.
You would have to copy paste. No, export as text.
Okay, great. Yeah. Now you have to change it to a graph, a table data, and then you export the data. Yes. But it is an export as it is text, not as a.
So then Excel can open text, or you can then save it as a different format from Excel, I guess.
Are you sure? Okay, great.
So what I do for my presentations is I print as PDF, and then I use the program called Illustrator. And Illustrator can edit PDF, so then I can remove text or icons or anything I don't want. But I know Illustrator, so if you don't know Illustrator, maybe that's.
Yeah, I know it.
So that's because then you can change the lines, you can change the colors, you can do all of these things. So I found over the years that is the best way because the data files in Excel are huge. Open, so you can go open with, and you can say choose another app, and I think you will find Excel here, or we can just go. Open, and then you can say, I guess computer, browse, and then you can say desktop, and then here you can say any file, and test export is here, and maybe you can say, or maybe it does it automatically. Yeah, it does the import wizard. So I guess it's delimited. Yeah, that's what you want. Tab delimited. Then you can say finish, and there you have time and intensity. So if you make a chart, insert chart, scatter, I guess like this. No, like this. There's the data. So you can do that if you want that way. Does that make sense?
Yes, thank you.
You're welcome. Okay, that leads me to one point also I want to show you. So, okay, we talked about the Explorer. I'll just get rid of this. So you can do that also for the spectrum. So you can say highlight the spectrum, and then you can say show, and you can say data and peaks table, and then you have the data from this. So you have data, which is every data point, and you have peaks, which are the main peaks, which are labeled. So you want to always, it comes from data, and then, but you're going to have quite a few lines. Okay, it's not too bad. So what you can do is you can see, also visualize the data points in any chromatogram or in any spectrum. So here it's just showing you one data point, right? This is the data point that we clicked on in the IDA Explorer. But what you can do here is you can say window, you can say graph selection window. And graph selection window brings up actually a lot of different tools. We can talk about those. But you have here this button, which is to show the point symbols. So when you click on that, now you see the individual data points. So these are the scans, right? That was the first data point where it was chosen, which is that data point, I guess. Let's have a look and see. So that one is just under 5E4. 5E4, yeah, it's that one. So that was the first data point that was taken. So then one of these must have been missed. Then two, and then, because that was the third one, right? Oh, I lost it now. 242 here. And what are we talking about? Around 8 minutes, right? So here we go. Where is it? Right here. So that's one. Not the same data. That's why. Okay, so this one is right just below 4E4. So it's that one. That's number one. So for some reason, it also missed the data point. It went to that one, which is there, and then that one. So it did do it 3 times, but for some reason, it didn't catch this data point as for MSMS. So
they are not interlinked together. And if you click into the upper graph, they will show it in the floor.
If you click in the upper, yeah, so these 4 are linked because these 2 come from the IDA Explorer, and I opened these 2 from these buttons. But this is separate. This is the one that came from analytics.
Yeah.
So we can't link this one to this. This one will always be here. But you see when I click here, these 4 all update. But
yes.
This one is not because it came out of analytics.
Exactly.
So we can see, so that is a little bit interesting why. I'm not sure exactly why, but there should be another data point right in there also. So it did here, skipped that one, and it did here, and it did here, and then it had 3, and it forgot about this compound. Why it didn't choose that one? At that cycle, there must have been 10 other peaks that were more interesting than this one. So that was chosen. It is doing a lot of processing very quickly, right? Each one of these data points, don't forget, is less than a second apart. So it has to process all of that in real time. It's not 100% perfect. It doesn't miss, let's say, 3 data points, but it is sometimes true that it will miss one like that. But there may be a valid reason that there was 10 other things at that time. Don't forget, these XICs, when we look at them, they really simplify the picture. So the tendency is to think, this is the only thing going on. Well, actually, no, right? There's many, many things going on. If we zoom out the mass range, let's zoom out the mass range and zoom in, right? So there's the data point we're at. So this is all happening at the same time. From there to there is 0.01 of a minute, right? So these are just these are fractions of a second apart. All right, so to show and to hide the data points in a general chromatogram or in a mass spectrum, you have this button, which I got from the graph information window. You can turn them off. If you want to see the data points in the mass spectrum, you can also see the data points. Go. So now these are time, right? These are the data points of the TDC data collection. So we can turn that on and off. Also in a chromatogram, you can make measurements about resolution and so on. I think somebody actually asked that the other day. If you turn this default info, here you have signal to noise. And now if we make a measurement of a peak, it will tell us things like peak area. Maybe we have to measure all the way. And then, yes, and as we choose a noise region as well, we will get a signal to noise measurement. So you have to choose also a signal to you have to also choose a noise region. So to do that, you guys can't see what I'm doing. Of course, I hold the shift key. So I highlight the peak, then I press and hold shift, and I highlight another region. And now I have signal to noise of this signal versus this noise. So if you want to measure signal to noise of a peak, you can do that. And I guess, yeah, sorry, in the mass spectrum, it will tell you the resolution. Yeah, there it is. So there's the resolution in terms of mass 23,000 of a particular mass peak that you highlight. So it gives you slightly different information if you're looking at a mass spectrum or if you're looking at a chromatogram. But you can calculate resolution or signal to noise, sorry, of individual peaks using this graph selection. Everyone remember where I got this from? This was under window, right? Window, graph selection window. All right, so I think that brings us through the let's say the manual data processing for IDA. We can take a look at swath data. Let's take a look at swath data, and then we can also get a feel for the swath windows. And then I think that's after that will be a good place to take a break, because this will be the break between the targeted analysis and the non-targeted analysis. And then we'll come back and we'll do the non-target analysis where we try to find these compounds without knowing their formulas. And we'll talk about formula finder, and we'll talk about doing the structural elucidation, which I think will be also interesting for you. And we'll do that the same way. We'll do it in analytics first, and then we'll come to Explorer, and we'll do that. So any question on interpreting IDA data? You will find this IDA Explorer extremely useful in going through IDA data, because you don't have to worry about which experiment the MSMS was in. Everyone can see how we export the data. Oh, sorry, I just saw that now. Okay, but you already asked that question verbally. Okay, fine. Any other questions? You've got to try it, right? You've got to go through and try it yourselves. Okay, so let's go back to analytics. So I'll close this. Let's go back to analytics. And what we'll do now is we'll take a look at the swath data. So we'll just choose a random sample, this one here, and we'll have a look and we'll see how to process the swath data in the explore mode. Now, what's happening here? Why do we have a red? Ah, great. This is what I was looking for earlier. Okay, good. So I can remember I wanted to show you about deconvolution, and I couldn't find an example. So here is a perfect example, and this will also lead us perfectly into explore mode. Okay, so when we look at this particular MSMS, we see that there is a pink spectrum as well as a blue and a gray. So we know what is the gray. The gray is the library. Now, the pink is actually the raw data, and the blue is what we call deconvoluted data. So deconvolution applies to swath data, and what deconvolution does is it tries to identify which daughter is coming from which parent in a complex MSMS by tracking the parent and the daughters over time. So maybe what I will do is I'll go to Paint, and I'll make a new paint. So what I'll do over here is I'll draw Q1. So this represents Q1. Now in swath, we have not a single parent going through the Q1, but we have the window. So let's say the window we're looking at right now is 200 to 250. And we have two masses. We have a blue mass. Oh, sorry, that would be purple, right? And the blue mass. Okay. So both of those fit through the Q1 at this time because they are in the mass range of 200 to 250. So there's no separation between them. We have two parents. So in the MSMS spectrum, here's the MSMS spectrum, okay? MS, right? And what is this MSMS of? It's of 200 to 250. That's the swath window, right? So in this MSMS spectrum, we're going to have the parents, and the parents are the same, okay? Right? Ah, sorry, not. Parents are different. Sorry, I got confused for a second. I was thinking terbutrin and prometrin. Parents are different mass, and I've color-coded them, and they both fit through the 200 and the 250 because they fit through the window 200. Right? Different masses, but they're both going through the window together. Now they're going to fragment, so the fragmentation patterns, I should say, fingerprints are going to overlap. So you'll see them like this, except we have no way of knowing which one is purple and which one is blue, right? I'll mark this P for parent. So I've color-coded it for you, so we can see that nicely. But in reality, in the data, we don't know. It's all a jumble, right? And we saw that kind of when we had terbutrin and prometrin. I mean, those are isomers. So maybe that's going to add another level of confusion to the explanation. Even you saw I was confused there for a second. The daughters are in the MS spectrum together, and we don't actually know okay, we don't know that this daughter here specifically comes from the blue parent. However, there is one way to look at the data over time, and that is what the deconvolution is doing. So the deconvolution takes all of these daughter ions and the parents, and it makes XICs. So let me label my axes. Never draw a graph without labeling your axes, right? That's what your geometry teacher told you. This is ME, and this is time, and this is intensity. So here we have chromatogram, right? This is XIC. Okay. So what we can do is we can look at the XIC of each of these parents over time. So I would draw that. So here's the XIC of the purple parent. And here's the XIC blue parent. And what we are looking at is the red line. The red line is this mass spectrum. So at that mass spectrum at the red line. So you see both parents are present and they overlap, so all the daughters are present also. So this MSMS spectrum is happening at the red line. By looking and making an XIC also for each of the daughters, we can then color code them because the daughters have to follow the same pattern in time as the parent. And that makes sense, right? The daughters come from the parent. So in terms of chromatography, they have to have the same peak shape as the parent. So all of the purple daughters will have this profile. And then that's how we can know that they are actually purple daughters. And blue daughters will all have this profile. In other words, no daughter can have a different profile than its parent. So by doing the deconvolution, we can now color code like this. And we can say, okay, this daughter here had a profile in time the same as this parent, therefore this daughter must come from this parent, not from this parent. That is the mass range. There's 200. There's 250. Does this make sense to everyone? This is called deconvolution, at least in terms of this data, swath data deconvolution. Deconvolution in terms of swath means that we make an XIC for each parent in the window and all the daughters, and then any daughter that follows the parent's XIC is assumed to come from that. So this exploits the slightly different retention time of the parents. Make sense to everyone? This also, yes? This also shows you how important it is to also have a good number of data points, right? If these peaks are poorly defined, meaning they don't have enough data points, then we won't be able to track very well how the daughters follow the parent. So the deconvolution only works well when you have good peak shape. So chromatography is important. And you have the number of data points set up correctly with your cycle time, so the peak is well defined in the mass spectrometer. So what the data is showing you is actually it is not doing color coding for each parent. It is doing color coding for these daughters follow the parent, and these other daughters follow some other parent. So you see that here we have the pink is the full spectrum, and the blue is the spectrum that's deconvoluted. The blue follows this particular parent perfectly. Now we don't have enough data points that it's not working exactly great. You can see the peak is very triangular shaped. So if we had a few more data points here, then this deconvolution would work a little better. As you can see right now, it's getting a little bit confused, and it's actually reducing the intensity of some daughters that actually should be from this parent. And the reason for that is probably a lack of data points here across this. So that's the deconvolution. There's no control for it or anything. It happens if the software can do it. And that's why you see when we have a good match from a nice strong peak like that, there's no deconvolution applied. So for simazine, probably the deconvolution is applied because the peak is not quite so strong, and there may also, it may have been determined that there's quite a few other other parents in the swath window. And that makes sense because simazine is also the smallest mass. So there will be more interference at smaller mass. So I'll just open it up for questions on deconvolution. And then once we've answered those questions, then I'll show you how to go to explore mode from this data, and we'll explore manually swath data. And we'll look at these windows. That's going to be very different than IDA. Everybody understand the deconvolution? All right, I guess that's good. I hope you all aren't asleep. All right, so now what we'll do is we'll go to explore mode. So luckily we have this handy button, right? So we can say open data in exploration. So let's do that. So now we're going to get those three pictures. So this is the XIC on the top. This is the TOF MS. And this is the TOF MSMS. Again, if you get confused, you can just read it from the top, right? And also take a look at the x-axis. The x-axis tells you very quickly chromatogram or spectrum. Time is chromatogram, mass is spectrum. And then up here it tells you, okay, what you are looking at. This is a selected ion chromatogram of 202.285. It's from analytics. This is a swath TOF MS. And this is a swath TOF MSMS. So first thing I want to show you in the swath TOF MS, let's zoom out. So this is the complete MS spectrum. Now the swath MSMS that we took, what is the window? You can read that in the brackets here. This window is from 200 to 250. So I'm just going to zoom in and I'm going to show you all the parents, right? So 200 is the minimum. So all of these parents in this blue box were chosen for MSMS together. See that? That blue box is the Q1 selection window for this MSMS spectrum in swath. So if we just go back to my paint picture, that's corresponding here to this window, right, to this window. So all of these parents pass, all of these ions that are in the blue box, represented here by the blue and the purple lines. So they're all going through the Q1 together, they're fragmenting together, and they're producing this MSMS spectrum. So this is not a pure MSMS spectrum. This is MSMS of all of these things. Now, where's 202? There's our 202, right? 202.0856, 202.085. Yes, so that's the 202 that we're interested in. But its daughters are going to be jumbled with the daughters from all of these other ions. And you see in this case, the 202 is by no means the tallest one, right? It might be the second tallest, but there's a lot of candidates that are pretty close, right? And we have a very strong 215 here as well, whatever that may be. We have no idea what it is, but whatever that may be. So all of those contribute to these daughter ions. So that's how you can look and you can see, okay, you know, why is my swath not working great, right? Here we have a red icon. We didn't get a good library match, right? Now that might be also because we sorted by purity. Yeah, see? So we remember we kept the purity as the sort. Purity is not great for swath. If we had sorted by fit, this would be green. Because the fit score is correct, you can see for every gray line in the library there is a blue deconvoluted line. So that is actually what we should have done here, is to sort the swath data by the fit score. But just to show you, okay, where are all of these other daughter ions coming from? Right, in this case we have no isomer, we have no other peak in the XIC, so it has to be coming from a different mass. Well, when we go and look at it in explore mode, here are all of the other parents that I drew in this blue box. Because this blue box corresponds to the window here of the swath, of this swath. And this is the first swath, right? Then the second swath, you know, it's 249 and so on. So does that make sense to everyone? That's why this picture is not so clean. So what could you do? Well, you could adjust your method, right? Maybe at this mass range with this sample, you need a smaller window. If you have a smaller window, like let's say you went from 200 to 225, right? And then your second window would be 224 to 250 and so on. So you'd add another window. That will reduce the complexity of your MSMS. However, it also takes time, right? Every window that you add is a new scan that takes its own time. So already in this case, we are pressed for data points. As you saw there, right? How do I show the data points again? So I go to window, right? And I say graph selection window, and I say click my little icon here for my data points, right? I don't have so many data points here on this peak. So if I start adding more experiments, then I'm going to very quickly run out of data points and not define my peaks very well at all. So this is the dilemma we face, and I guess also comes down to chromatography, right? Narrow, very, very narrow peaks are not a good thing on this instrument because we don't have enough time to do all the experiments we want to do. So this peak is even 6 seconds, right? Here's 0.1 and here's 0.2. So 0.1 of a minute is 6 seconds. And if you remember when I was talking in the lecture and also yesterday when we were talking about method setup and so on, I was hoping to have 10 to 12 second wide peaks. So we should perhaps reduce the flow on this column a little bit and lower the pressure and get a little bit wider peak in order to have a few more data points. Does that make sense to everyone? Everyone understand why we have a red mark? Data is actually false, right? Shouldn't be red. That should be a green check. It's because we did several things. Well, the number one thing we did wrong is we didn't sort this data by fit score. We did it by purity. So it's using the same criteria. Yes, yes.
Can we adjust here the type of the purity to change it to fit and reprocess it here, or is not?
We
it
can't
cannot be done here.
It can be done, yeah. Let me show you. So you can't do it actually from here like you could with the integration parameters, but you can go up to process method, and then you can say edit embedded method, and now you are actually editing the method which you use to make the chart, but again, you're editing the embedded copy. You're not editing the main copy. And so we can come here, where was that? Under library search, right? Library search, and then we can change this to fit. Yeah. And then we can say process and close. Note, you're not saving here. There's no save, just process and close.
Okay.
Right? If you want to save, you have to go back to process method and choose save embedded method as. All right, so now, now do you remember what was the sample? I don't remember the sample. Is it this one? You know what? We can look at the name here. So here's the name. So it was 24 ZK322F2. ZK322F2. Yeah, it was this one. Oh, why am I seeing graphs? Okay, so yeah, there it is, green arrow, right? Or sorry, green check mark. But now it's not deconvoluted. It's not deconvoluted because it's sorting by fit and it got a very good fit score. But no, this is not, something is not right. Maybe it's this one. Yes. Yeah, is that right? CE, right? I missed the last, yeah, CEB 24. Yes, and it is 24. Yeah, it's this data. This is the data. Sorry, not the other one I showed you. This data, and this was the peak here, simazine, right? So we have the same deconvolution. There's the bad purity score, but now it's sorting by fit, which it should be for swath, and so we have the green mark.
Okay. Thank you.
Welcome. So that's the main differentiator in your processing methods between IDA and swath. Basically, everything else can be the same, just your how you sort your data. IDA by purity and swath by fit. And everybody understands why that is, right? Swath is not clean MSMS, dirty MSMS.
Yes, it's clear now.
Okay, great. All right, so we looked at just that one window. So if we want to see the other windows for swath for this experiment, we can go to show and we can go to XIC, same as for IDA. And now again, we have the 11 experiments. Now it's totally different. It's only coincidence that there's 11. And that's because I set it up to be the same. I set up my IDA to choose 10 ions, and I made 10 windows in swath, plus the TOF gives 11. Now, why did I do that? So that we have a good comparison between the methods. The timing is the same. 11 scans will take roughly the same amount of time. But that is not something by coincidence. We did that because we set up the methods that way. So here you can see this is coming from experiment 2, which is that XIC. So here you see the window in the brackets, right? So if you wanted to look at another window, you could pull that up, for example. And now this is the XIC. The one that opens is in gold, right? Always that's the one you're using. If you open up that XIC. Now you see the XIC for that experiment. So you can do all the same things that you could do before. Double click, and then move to a different retention time. You can see the mass spectrum at that time. So there's no IDA Explorer because nothing is being picked and chosen. It's not random. It has these windows that it moves through. So for this, we need to look at the individual XICs for the individual windows. And then what you can do from the XIC, or sorry, from the mass spectrum, is you can highlight, for example, a certain daughter ion, double click, make the XIC of that daughter ion, get the same message, right? Because you're doing it manually from the spectrum. It's finding the width of the XIC based upon the width of that peak that you highlighted. So say OK, and then takes a second. There is the XIC. Now this is a very special XIC. This is coming from the swath MSMS. You see it here now, swath MSMS. This is not an XIC of the parent. This is an XIC of a daughter. So for those of you who have done something like MRM, multiple reaction monitoring, on a triple quadrupole, this data here would be an approximation of how to do MRM on a TOF. We don't do it through setting up an acquisition method. We do it by processing the data in swath mode and then looking for a specific daughter ion. And you see actually the trace looks very similar to the MRM with very characteristic low background. Make sense to everyone? All right, I'm just reviewing my notes. And if you remember when we just started this morning, I said, oh, there is a problem of retention time with Amitrian. Remember? And then that one sample, and then we went through it, and then we saw actually there is not a problem. But that one Amitrian chromatogram had a double peak. So let's go back and look at that. That'll be the last thing we'll do now here before we take a break. And then we'll take the break, and then when we come back, we'll do the unknown processing. So any questions? Everyone doing okay? So I think that was in this sample with Amitrian. And then when we were looking, I don't know which sample I chose for the representative sample. These all have one peak. There it is. All right, so here's an example where we need to do a little bit more exploring, let's say. So this is a sample. I'm not sure what's this sample, but it's spiked with Amitrian. And we look for Amitrian, and we know this is the right retention time from the other samples. But let's say we didn't, okay? Let's pretend. And so you have these two peaks. So how can we investigate which of the two peaks is correct? So first thing we can do is we have selected this peak, and we have 3 green icons. So obviously retention time is not truthful here because we don't know. We're pretending we don't know. So don't look at the retention time. But the mass error and the isotope confidence is very good for this peak. So what I can do is I can select also this peak now, and it will jump to that peak. And do you see what happens? We get a red error here. So why do we have a red error for this peak? So this peak has mass error 14.4 ppm. Now, we didn't actually discuss this too much because everything is green and this instrument is really good on mass accuracy, so normally everything is okay. But 14 ppm mass accuracy for this instrument is almost 10 times outside of the spec, right? The spec is 2 ppm. So as you see, all the other compounds, great mass accuracy, in fact, even below 1. But here we have 14, so it's clearly not right. So just by switching to that peak and taking a quick look at the mass accuracy, I know already it's not right. Now, what else can I do? Well, I can look at the isotope pattern. And this is a little bit unfortunate, but we get a green for the isotope confidence. So let's take a look at this mass spectrum in a little bit more detail. So what do you see here? You see that this is the 228, and there is exactly a 227 here. There shouldn't be a 227. A metrion, the ion monoisotopic is 228, but this has found the C13 isotope of a compound that is 1 Dalton lighter. It's a completely different compound with a completely different formula. It's off by 1 hydrogen. However, its C13 isotope is then only 1 Dalton difference from the all C12 of a metrion, and that mass accuracy is within 14 ppm. So that's a metrion, you could say a metrion minus hydrogen and 1 carbon 12 changed for carbon 13 would give you this peak. So even with that, let's say, relatively small mass difference, we're still able to say clearly that no, it's not correct. So that's an example of a misidentified peak. And this happens a lot. So I urge you to look at the isotope pattern and pay attention if you are following the C13 isotope of another compound that's different than yours, but different only by 1 hydrogen less. Because you will face this problem. It's relatively easy to tell. You'll have a mass accuracy roughly, let's say 15 to 20 ppm off, which, guys, it's completely unbelievable. This instrument, there's no way that, unless something is really wrong.
ألو أهلا علي، كيف حالك؟ إيه أكيد، إيه أهلا وسهلا.
Correct, but it's misleading because you're actually following the C13 of another compound. Does that make sense? So that actually, I caught that this morning by seeing the 2 peaks in the XIC, right? So how wide is the XIC? The XIC is 0.02 wide, 0.02 Daltons wide. So the XIC is just catching this compound. That's why it shows up in the XIC. Showing up in the XIC is set a lot wider than ppm mass accuracy. So actually that goes back to the training. Let's take a look at that in the lecture. So if you remember, I showed you this slide. Let's go and look at this slide. Where did we talk about isotope? Oh, yeah, that was it. I just saw it a little bit. Next slide. Yeah. So look at this slide, right? So this is a 2 ppm mass difference. 0. Well, let's have a look at what mass are we actually looking at. What is the mass? 228, right? 227, 228. But it's right in between. So this is 136 to 300. Okay, it's closer to 300, right? So, it's roughly. All right, anyway, this is a 2 ppm mass difference, plus or minus. It goes from here to here. And this total width is 0.0006 Daltons. We are producing an XIC with 0.02 Daltons wide. So that's why occasionally we will get other compounds in the XIC that are just caught on the edge, and they still give us what looks like a beautiful XIC. But when we actually go and look at the true mass, to the top of the mass peak, then it's 14 ppm out. It's clearly out. So don't trust just the XIC. Look at this. That peak looks equal to that peak. How we can tell the difference, right? Have to focus on the MS. The MS information clearly says this compound is not found. Does that make sense to everyone? I realize it's it's heavy going, but I tried to show you this morning some good things. I mean things that worked, but also we tried to investigate all the red and gray marks that we saw, so that we know what to do and how to interpret that it is really wrong. Anybody have any questions? Any comments? All right, so we'll finish the morning session just a touch early, 14 minutes early, and hopefully that'll give us a little bit extra brain power for this afternoon, which will be, I think, even more tough than this morning. So this afternoon, what we'll do is we'll process the same data as if it's an unknown sample, and we will try to look for these triazines and try to find them as if we don't know that they're there. Now we will use the spike sample. I'll explain that why, just so that we do actually have something to find. And we'll compare it to the non-spike. So we'll approach it in that way. And we'll do it the same way. We'll do it in analytics first. And then we'll go to explore mode, and I'll show you how to do it in explore mode. And we'll talk about formula finding, and we'll talk about structural elucidation. And then I think that'll be a good finish for the first week. We will have covered all of the tools at least once, in a very basic way, yes, but we will have covered all the tools at least once, so it'll give you a good foundation to start practicing on your data yourselves.
Alek, perhaps we can also try to search for one of the compounds and the unknown which is not from the triazine mix, to match it. To try to match it to the library.
Yeah, sure. That will happen by default because we will pretend that we don't know.
Sure.
We don't know that the triazines are there.
Correct, but I mean, even the one which is not spiked, to try to find some of the compounds of.
Yeah. Okay. So then you need it. So actually, we didn't discuss this yet because we just said run some samples. So that could be, I guess, a little bit of my fault. So the unknown processing works by comparing two samples, and the only thing that should be different are the compounds that you want to find. This will be perfect because we will say, okay, XA, for example, is the not treated, and the hex B is the treated. So it will look for differences between those two, and the only thing that's different are, of course, in this case, the compounds we added, the triazines. So I guess in a short way to say that would be, we need to run some kind of blank, which is basically the same extraction, but without the compounds you're looking for. So maybe you have that already, I'm not sure, but would one of these be an appropriate blank? Like, is F2 a blank for CE, for example?
Well, we have to ask the guys who placed the samples there, which is Ghada and Basil.
Yeah. So
We'll, if you want, we can ask them during the break, and then we'll get back to you once we come back.
yes, okay. So they are not here with us.
They are here, but I'm not sure why they're
Oh.
not responding.
Okay, I see. All right. So yeah, just to explain that, I guess in a little bit more detail. So and actually we've shown it today, right? I mean, look at these chromatograms. You know, when you look at this, right? What are all of these peaks? This is an extremely sensitive instrument which catches so many compounds. So all of this is in your sample. So you have to know, okay, which one of these peaks is actually interesting. And the easiest way to do that is to have a comparison of two samples. And so this is different. And then because it's different, that's my target that I want to go and look at. So you can imagine when you, I guess, I don't remember exactly, but I guess these are bacterial extracts, right? I think so. If you have a bacterial extract, you know, those sample is full of molecules, a huge number of molecules, which by nature should be there, sugars and fatty acids and amino acids and all kinds of compounds, right? Plus anything that you happen to have introduced during your sample prep. If you put it in a plastic tube, there'll be plasticizer there and so on. So the idea would be to have, okay, the bacterial extract which is clean, and then the bacterial extract which is treated by your experimental conditions, whatever they are, and then carry those two through exactly the same sample prep and everything, and run them in, as separate samples on the instrument. And then the only thing that's different are the compounds that you want to identify. So that would be kind of the workflow for the unknown. Now we're going to do it with the triazines, and like the gentleman said, we'll do it with other samples too. We can certainly try. It's just a processing exercise, no worries. But to actually find something in samples that don't have that good blend to compare it to is really difficult. As you can see, the task is huge, right? We looked at the ID Explorer, we saw all of those dots. You have to investigate each one of those dots. So if you can exclude 99% of them because they're the same in both samples, it makes your life so much easier. Does that make sense to everyone?
Yes.
Now, I think now you're starting to see how complex the samples are. Even if you think you simplified it, it's still a very complex sample. So that will give you something to think about. And you know, all the software tools are here. It just takes, of course, time to go through it. Okay, so I think we have a good plan then for after the break. So I will see you all at 1:30. And we'll do the processing like we said, the spiked and the non-spiked, and we'll do it first in analytics, and then we'll continue in the Explorer, and I'll show you how to use both tools for formula finding and for structural elucidation.
Okay, great.
Good? Okay. So enjoy your lunch or whatever you do for 1 hour, and I will see you back here at 1:30.
Okay, thank
All right,
you.
perfect.
Okay.
Thank you, Alek.
You're welcome. Okay. Bye for now.
مش الحالة عم عامل ريست للباسورد بس هلا عم بشتغل على اسم النتورك. سلام مازنو. هلا مش الحالة عم بتقول ريست للنتورك بس هلا سلام مازنو مش الحالة عم بتقول ريست للباسورد هلا عم بشتغل على اصل النتورك في مشكلة بالنتورك.
There we
هي
go. Now you
الأساسية.
can hear me? Good afternoon.
Good afternoon, Alek.
فممكن
Yes,
تعوق
good
شوي.
afternoon. Sorry, I was on
هلا
mute.
قد ما في رح احاول بس خلص ويجي
Alright.
عندك.
So Bomgar is still working, but we have the new teams. Okay.
Well, Alek, I just
Mhm.
wanted to ask you if we could possibly start now our session with perhaps processing some of the tracing data when we click them from this end here. You're seeing my point, right?
Oh yeah. So from here you can only go. Yeah. Sure. So but you only open in Explorer mode. There's no way to open in Analytics.
Exactly. I mean,
Yes.
is it to start from
Sure.
from
Yes.
the queue and then try to find the as if we don't know what are the mix of pesticides here and trying to find them starting from this end.
Yeah, right. I mean, that's basically what we're going to do right now. We didn't talk about that yet as unknown. Maybe we can just have a discussion about that part when everybody joins. That's an important point. So, I mean, to answer your question, there are basically 3 ways to open a data file in Explorer mode. One is to double-click from the queue. One is to open Explorer mode and to say File Open. And then one is to use the little button in Analytics to take that data to Explorer. So those, that's the short answer to your question. There are 3 ways to get to Explorer.
I mean, it's good for now to start with going to see it from the queue and try to find the pesticides from this end here.
I mean,
as if we don't know what are the different pesticide mixes inside the pricing mix, and trying to find, for example, that pricing which is present there from this end.
yeah, so I would say that's going to be close to impossible. That's just not the workflow. I mean, unless you want to open the file in Explorer mode and proceed. But
it's not like selecting, double-clicking, and then zooming here and selecting.
Sure. Right, but look how difficult that is. Yeah, so what is that, right? I mean,
yes, exactly. I mean, how can we go from here finding the molecular weight of one of the pesticides from here? Is it possible? That's my question to you.
Sure, so that's what we're going to do now as part of the unknown. So that is unknown analysis. And we'll talk about Formula Finder, and we'll talk about the in silico fragmentation. But the most important step of doing unknown analysis is to find out what is my compound. So you raise an excellent point, and that is really the point of the most difficult part of unknown analysis is finding what it is to analyze further. So just keep in mind, so did everybody understand the question? The question is, in essence, the question is like how to get started in unknown screening or unknown finding. And that goes back to what I was saying also before we took the break, is that you need to really have the controls correct. If you, ideally you will run 2 samples, and those samples will differ only by the thing you want to discover. For example, I use the example of the bacterial culture, and then you have a bacterial culture that is treated with something, and you have a bacterial culture which is not treated with something, and then you want to find out what does that treatment do. So that's the difference, and you need to process those 2 samples exactly the same in parallel. And also inject and run on the instrument exactly the same in parallel, and then the software will compare them. So you have to think about. Yes, sir.
Hi.
Hi.
This is Tony. So I have a question regarding this.
Okay.
What we usually do, or what we used to do, we used to have a standard sample, right, that contains 3 or 4 compounds that we know what they are. We would run that sample by itself without any bacterial cultures or unknown compounds, and then we would run the unknown compounds afterwards we check with the known sample that the compound that the run is fine.
الحقيقة اللي بعتقد
But
كمان ما
because
مشي
mostly what
الحال
we have is
نزلت الريجستوري
99.9% of the molecules that we're running on
فنحكي
the
معنا
SCIEX
مثل
are unknown compounds.
على طريقة ثانية
And one of our
وإن شاء الله
aims is
أنا
to actually
بعد التنتين بس
build our own
تواصل
database.
معي
Retention
هلا
time,
إنه خلصنا من
MOPZ, MS2DM, UV spectrum, yada yada yada, for each mass that we find. And whatever we
سوري
do,
يعني كثير عم ياخذ من وقتك
No
بس
problem.
إنه عم نعمل
we
عندنا
try to come out and follow this bio-guided fractionation. Now, if for every sample I am meant to prepare a duplicate and have a control for one sample and not for the
يعني حلو
other,
نرجع
you're talking
ننزل
about my
ايمج بس
experiment
نرجع
is costing
ننزل
10
صحيح
times
صفحة مرة
more
ثانية
مشكلة
مشكلة
حتى هيدي
So
موجود
what we
عليها
used to do,
النيم
we used to prepare, for
كمان
example, we take
حسب
the case of thiazine.
فعم نحاول
You would prepare a standard case of thiazine. You know how much that is, you know what's the molecule in there, you would run it, and then you would run 10 samples of your unknown compounds. And then you would run a blank and then thiazine again, and then 10 samples of your compounds. If your thiazines in between and at the start and at the end are fine, then your run is okay. But then you can't double click on whatever spectrum you've generated from an unknown sample and investigate that by yourself.
Absolutely, yes, you can. There's no, and that's what we're going to do right now. But look how many. So okay, I'll show you. Let's do that. Okay. So here, so actually, the beginning of what you said, I completely agree with. You should have some spiked compounds into your samples, and run those samples as an extra sample. And that is what I encouraged all your colleagues to do, and that's what they've done with the B sample. So the B sample is with the triazines added, and the A sample is without.
Okay.
All right. So perfect. So here we go. Let's. You want to try with the triazines first? Why not? Okay.
Yeah, why not?
Okay. So here it is, right? And this also goes to the other gentleman's question as well. So here is the sample run. I'm going to double click, right? Here's the okay. So when you open an IDA like this way, you have the option. Do you want to see it as the IDA Explorer, or do you want to see it as the TIC? You have this option.
Okay.
So we'll do both ways. Okay. Well, first we'll do the standard TIC. So here is your TIC. Now, I can almost guarantee you that we cannot see the triazines here because we know they show up right here, 7 minutes, 8 minutes, right?
Okay.
So here's the TIC. This is, don't forget, this instrument is incredibly sensitive, right?
Yeah.
So maybe it's working on a sensitivity level that's a little bit different than what you're used to before. So this is the TIC that opens, and remember we discussed it a little bit this morning. I understand we discussed a lot of things this morning, so I will try to say it twice if I can. So you have this double-headed arrow, and this double-headed arrow, when you click, now you will have the individual TICs for each experiment. Okay. So in our IDA, we have 11 experiments. The first one is the TOF TIC in blue, and all the other colors are the individual ticks from the IDA. Okay. So what I would do is I'd get rid of the IDA right now, because all of my parents are going to be found in the TOF. And the TOF is really where I'm going to look and identify the parent, and the IDA is only really useful in a library search or in a structural elucidation. So I right-click, and I say remove all the traces except active. And I don't actually need the full TIC at the top anymore, so I'll just hide it. All right, so now we're looking at the tick of the sample, the top scan.
Yes.
This is the problem. What do I start looking at, right? I don't have any peaks here. I can't even see the triazines, right? So
right, but you have a tick peak at 14.905. Can you see what's the mass under that?
Yeah, absolutely. So we know how to do that. We double click, and then we move this bar, gray bar, to that mass, or sorry, that peak.
Yeah.
And then these are the masses that make up that peak.
Okay.
So now what you can do is you can, from this, you can produce an XIC, right? So do
Yes.
I want to see which one of these masses
So
follow
the 763.601.
Okay. All right. So highlight, double click. And for those, if some of you are a little lost because we're going a little bit fast here, all of this stuff is in the tutorial as well, right? Actually guiding you step by step to do. So there is your XIC. So that does look like a compound, right? That looks like a nice candidate.
Yes.
So my point is, we have identified a compound, and that is actually on the most simple level. So why do I say that? And you probably know this, Tony, but maybe just for the benefit of the other people. So on the LCMS system, what is the most simple indication of a compound? And that is that it chromatographs. And when something chromatographs, it forms a Gaussian peak shape, exactly like what we are looking at here. Just as an example, and before we continue, let me try to find something that doesn't chromatograph, or it doesn't chromatograph nicely. Let's have a look. I can do it. So we find so many nice things.
Well,
That's also
this would be from the same molecule. No, the retention time is different, isn't it?
Yeah, I'm not sure that's true.
I don't know. That's a different retention time.
I think maybe we have here some. I think these will all be plasticizers, but let's have a look and see. So there's an example, right? I found this mass at this retention time, but I get this TIC with a different peak here and quite high background. So that may not be a candidate. But I'm trying to look for, actually your data is really very good, I have to say. I'm trying to find something that like smears. What I'm saying.
You go, yes, maybe you go to minute 1.5.
Oh, okay, yeah, earlier, yes. So you see like that, it's not so great, or something that's very high all the time. But actually, I have to say that I'm quite impressed here. Everything is pretty nice. Sorry. The internet speed kills me. Okay. Yeah, so maybe a 372. Yeah, so something like that, right? So you guys see that? Let me delete these other ones that we put. And so we wanted to go with 760. So you see that would be something that would probably, I mean, we could perhaps even do formula finding on it because it is a mass peak, but it doesn't chromatograph very nicely. So it's going to be on the borderline edge of what you could detect from the system. So in other words, if you can't chromatograph it, it's not going to show up in your results. So what the automated way of doing this does is it automatically goes through the data and finds every mass that makes a Gaussian. That's what we're going to see. And then we can sort that list by signal to noise and by area and by intensity and so on. And so we can get, instead of choosing manually like we did, which there's nothing wrong with that, it's just, it's going to take you forever. I think you're going to find something interesting very rarely that way, because there's going to be so many compounds that behave that way.
Until you see the crude extract then.
Well,
this is a semi-pure sample. The crude extract is going to be full of peaks from minute, say, 2 until 18 or 18.5.
All right. If you can do that, that's excellent. But just be careful about overloading the system and so on.
Oh, absolutely.
If you can see a peak in the TIC, I'd be a little bit worried. But okay. I mean, if you see the peak in the TIC, your job is easy. So actually, the group who gave the plant sample for the demo, you could see that compound in the TIC. So if you're going to work on that level, then yes, you can go directly to the TIC and find it. But the software is designed to find things at much lower levels. Okay. So maybe you will be impressed with the software at the level that what it can find. So for example, keep in mind that we cannot see the triazines here, right? You don't see them. Okay, so having said my little spiel, let's continue. So with this compound, and so actually what we did is we double-clicked here, right? So we had this data. So we double-clicked here, we identified this 763 as a potential target, and then just to make sure we produce the XIC. So you can go from this software directly to the formula finder. You have under show, you can say formula finder. Now you open the formula finder feed. So don't forget, what is formula finder? Formula finder takes mass information and it tries to match a formula to that data, and it tells you the ppm mass accuracy. So what I do is I come like this, come up, move this over. Okay, so this is the mass we're interested in. And if a peak is not labeled like that and you want it to be labeled, you just have to move this blue arrow there. Yeah, all right. So now what you need to do is linking. Linking are these other buttons that you find underneath the truck. So you have a link to the MS and you have a link to the MSMS. We don't have the MSMS open right now, so we'll just start simple with the MS. What you do is you click and you drag this to the spectrum. And now the formula finder is linked to this mass spectrum. And whatever I select in the mass spectrum, now it shows up in the formula finder. So you see, as soon as I got a warning message, but as soon as I did that, I saw here, you see the 4 peaks showed up, that are the 4 peaks here that are labeled. Okay, so it's telling us that it can't find a formula. And probably the reason for that is this is a bigger mass and we don't have enough elements. So if you remember, formula finder is using the periodic table, and we talked about that chart of the nucleotides, right, on Monday when we started. That is the chart of the isotopes of each element and their relative percentages. So this software, it knows all of that. It has all of that in its memory. But in order to simplify the processing, we simplify the periodic table. And this is the maximum elements that the software will use to calculate your compound. So if your compound is bigger than this, it will not find. So maybe we need to just add a couple more carbons, and then we can say find. Still, it cannot do that. So maybe here we need to choose MH plus. There we go. So sometimes it gets a little bit stuck and it doesn't find the right ion type in this pull-down menu. Also, if it has identified a potential ammonium addict or a sodium addict or a potassium addict, you will also find it in this pull-down menu. So here are the potential formulas that match this data. Now keep in mind we are limiting strongly the periodic table. So if your compound has a phosphate in it or a chlorine or something, that's not here in this list, it will not find it.
But that's obviously to figure out if you have a chlorine or not, you can look at the isotope pattern of your mass and tell.
Correct.
And also you check the compound whether it's doubly charged or not, because the difference between the first peak and the second peak is a hydrogen. And that's fine, that's not doubly charged. The difference is not half, it's 1.
exactly correct. So the other people, we didn't talk about that yet, but definitely we spent a lot of time with the group on chlorine atoms. So yes, you and I, we can look at this and we can see, okay, this is not a chlorine isotope pattern, so there's no chlorine here, yes. But just as a point for the basic guys, if you do see that and you don't have chlorine in your list, you won't find it, obviously. So you can just keep it defined. All right, so this is a pretty good candidate, I would say.
Sorry, Alek.
Yes, yes.
Sorry, can you please repeat once we try to bring the formula and its phase to solve, from there, how do we get this table of the formula?
Sure. So just to remind everyone, show formula finder.
Yes.
Right?
Okay.
Now, if it's gray now. It's because I don't have a mass spectrum selected. You can only show the formula finder when the mass spectrum is active. See that with the gold? So now formula finder shows up. Now the first thing you want to do is to link.
Yes, after linking and then but it gives us a message that it couldn't get the formula.
Yeah, it was
From
because in this pull down menu here, ion type, I had not selected the ion type. It was blank.
Oh, okay, I see.
Yeah. I think that's a problem because this is maybe the first time we are using the software. So maybe that will not happen again. But here under this ion type, it was blank, so I had to select MH+. And also if it has detected the possibility of other adducts, so it will detect if you have maybe a sodium or a potassium or a ammonium adduct, then they will be in this list as well.
Oh, okay. Thank you, Alek.
You're welcome. And also you need to select the ions you want, so they need to have a blue box. Yeah, so it's done it again. You see it has the same message, so then I need to come here and do that, and then press find. Now it's okay.
Okay, thank you.
Alex,
Yes.
can we try to pick the other two molecular formulas and see whether they match better than this one or not?
Right, exactly. So they are ordered by the match. So by definition, anything lower in the list will match worse. If you click on it, it will show you here in pink. The pink is the theoretical isotope pattern of this formula that you've selected. So you can see, okay, first of all, the error is 5 ppm, which is not reasonable for our system. And the isotope pattern is shifted also. And then the next one is less error, but probably the isotope is more, yes. So even 2.9 at this good, nice, strong signal is not believable to me. So by MS only, that would be the best fit.
And this makes sense from what we've seen in NMR as well. There is no nitrogen, it's not a peptide, and RDB is 15, so that's 15 double bonds, if I'm not mistaken.
Yes, or their equivalents. So,
Yes.
Like
Or a C double bond O.
Right. So you know this.
Yes.
Ah,
I do.
okay.
I'm not sure about the rest, but I like it.
All right. Okay.
I'm just telling you what would be useful for all of us, because even the people who try to identify the pesticides, it's not only good for them to know the mass, but they want to know which pesticide they're looking at, if I'm not mistaken.
Right, absolutely, yeah. So, I mean, I'm surprised if you are, if all of your samples are this good, you guys are living in easy street, man. I mean, most customers I'm working with are looking for something, let's say 1,000,000 times less than this. So we are in E8, and they are looking in E2. So if this is how it is for you guys, yeah, you guys are gonna really love this instrument because it's gonna be so easy for you. Because does everybody understand why I'm saying that? Because this peak is standing out in the TIC. Just let me show you the triazines, guys. Look, so this is the triazines. I spiked them at 50 ppb. Here they are. I'll just do a extracted ion chromatogram. There they are, right? All the colors. but you don't see the peaks in the TIC, right? See that? So you wouldn't identify them as easily as Tony has found this thing here. So even this level, I'm going to go through and show you how to find this. So you can
Alek,
work with this level. Yes, sir.
Just for us not to, how do you say, to overload the device. And E8 concentration is okay. What
No.
would be the limit?
No, no. If you can work in 7s and 6s, it's better.
Okay. All right.
This is okay, but I'm a little bit worried that you'll start to have a carryover if it's sticky from like the auto sampler.
Okay.
The mass spectrometer itself really has no place for dirt to get. What I'm primarily concerned about is overloading the LC.
Okay. All right.
Yeah.
Let's
So
take
maybe,
this up.
yeah, maybe you can try the sample. So a good thing maybe tomorrow, because I'm not going to be with you tomorrow, is that you guys could re-inject at 10 times less. And also you do the same thing with the triazine spike, like I suggested, just to have something to play with and see how easy it is to identify it then. Because I think 10 times less is going to be a little bit more reasonable for the system as a whole. Even though you see the mass accuracy in terms of the mass spectrometer is great. Okay, so let me hide my triazines. But does everyone see that, right? Or does everyone not see that, actually? So you can't see these peaks in the TIC, right? But you see them so clearly when we look at them as extracted ions. So that's really, so my goal is to show you guys how you can identify something at this level, as well, of course, as identifying it at this level. All right, so I'll just hide that. Okay, so you can see here from the formula finder that we have 2 empty columns, and that's because we have not yet incorporated the MSMS data. So what we need to do is we need to find the MSMS data. Now, if you're coming from analytics and you click that little button, of course it opens for you automatically. But now we need to go and find it. So this is an IDA sample. What is the easiest way to find if MSMS is done on an IDA sample? We have the IDA Explorer, right? So I'm going to hide the I'm going to hide the XIC down here. And what I can do is I can go to Show IDA Explorer. Now we are looking at this dot plot, which we spent quite some time this morning looking at, right? So how am I going to use the dot plot? I know my target is 763, and I know the retention time, 14.9. So if I have those 2 pieces of information, then very easily I can zoom in and find that. So where will 763 be? 763 is going to be right here somewhere. And then my retention time is 14.9, so it should be somewhere right here. 14.09. Oh, whoops, sorry, 14.9. It's almost 15, right? I'll get there in the end. Give me a second. Here it is, right? And look, that's really nice. We have nice dark color. We didn't actually talk about the color of the spot, but you see some spots are very light and some spots are very dark. So the dark color has a better quality, which means that it has strong daughter ions in the data. Oh, that's weird. Huh? It gives just 1 daughter, which is half. So here's the MSMS spectrum. That's for me, that's a little bit unusual. You see, there's just 1 daughter. So I'm just checking times 2 is 786. So it's not quite perfectly at half. Okay.
Well, if for the fatty acid, it can break at a very specific point, hence you don't have too much of fragmentation.
Correct.
If it was a peptide, you would get amino acid sequences. If it's a polyketide or a fatty acid chain, it would be able to break at a very specific point.
And look at that. Those might be, that's a very strange isotope pattern, so that's not an isotope, right? And plus this is IDA, so maybe those are your 2 fatty acids.
Yes.
That's interesting, they're different by 1 Dalton. Usually, because that's not even a level of saturation, right? Saturation would be a 2 Dalton difference. interesting. Anyway, you probably know more about it than me. I'm just making guesses here. So, okay, so let's continue in the software. So what are we trying to do? We're trying to get a better identification of this formula. And we can do that through the MSMS as well. And as I mentioned here, these columns are blank right now because we didn't find the MSMS data. So what we did is we went to the IDA Explorer and we've identified this parent as being this parent. Actually, sorry, it's not correct. It should be this one, right? 763. This is 764. So not only do you have a, oh, wow, this is kind of cool. Okay, so you see that you have two very strong parents right next to each other that differ by 1 Dalton. Here's 763 and here's 764. Let me see the XIC. So from here we can see the XIC, right? You remember that from this morning. There's the XIC of that one, and there's they actually co-allude at 1 Dalton difference, 6-0, but it is not the.
I'm gonna put it on your cheek, okay?
Because it's 764.65, right? And here we have 60. So it cannot be. They cannot be the isotope pattern of each other.
Okay, are you ready? I'll turn it on and you say hello. You gotta talk. Okay, hold on. Yeah, that's it.
No. No.
Is that cool?
Interesting. So we
Try
can
again.
I
also.
was actually about to just ask you, could there be another mask down the line under that too? That
Okay, so you
could
put
give
it,
us.
you gotta find a soft spot on your neck, okay? You put it on there and you say, and then you could also say, I'm 5 years old. Can you imagine?
No, I didn't look at it correctly. It is the isotope. I was looking. I guess no, that one is 6-0. Yeah, not 0.0. Okay, sorry. Sometimes I get a little confused with my numbers. It is the isotope, right? So here's 763.6 is this peak right here, and this is 764.6, which is this peak here. Maybe it's just so intense, and that's why it's a little bit off in the second decimal place. Because here we have 0.60, and here we have 0.65. So they are the isotopes of each other, but you have this thing at 783, which looks quite similar and has the same fragment, which alludes a little bit earlier. So those two could be related. What is that difference? 783 minus 763. That's 20. And 20 is weird. All right. Well,
Once it can be H2O, no?
H2O would be 18.
That's it. Okay. You gotta get it on your neck.
But it could be a water and a double bond.
Here you go.
Anyway, step by step. So we'll stick with our original masks here, and now we have the MSMS here. So what I can do is I can use my MSMS link the formula finder to the MS as well, and release, and then say find again. Now you see that the MSMS information is also populated. You have a mass error for the MSMS, and you have a ranking based on the MSMS. So, how does the MSMS information play a role without knowing the structure? Right? At this point, we have no structure. So, what the MSMS information does is it confirms that the formula is correct based on the principle that this fragment ion here came from this parent here. So therefore, this fragment has to fit a formula that comes from this formula here. So if this formula is the parent formula, its daughters have to be pieces of this. So an extreme example would be, let's say, this has 3 oxygens, right? The daughter cannot match a formula with 4 oxygens because that doesn't make sense. That fragment could not come from that. And you can see that under the MSMS details tab here. So right now we've been looking only at the MS details. You can go to the MSMS details. And what happens in the MSMS details is that you have these little dots. It's a little bit hard to see in the gray color. What can I do? I can make this lighted. All right, so you have along the x-axis, you have the mass. And in this case, there are only 2 fragments. There is 393 and 281. So we see them here. Here's 393, and here's 281. And then you have different dots, and each dot represents a potential piece of this formula that we've chosen for the parent. And if that formula is correct, it shows you the mass accuracy away from 0 compared to the data that we have found. So actually, in this case, that formula, C53H7803, doesn't really give any good candidates because these are all more than 5 ppm off in terms of accuracy. Now, it could be that we're just too saturated here, and this is finally affecting our mass accuracy. But I wouldn't expect the MSMS to be out by more than 5 if the parent is really 0.6. It also could be, of course, that these fragments are some kind of interesting rearrangement, which it doesn't know about. Just to check. So these all actually... So it's not able to match any formulas without nitrogen. That's the problem. It doesn't mean it's wrong. It just means that it's a little bit more complicated to interpret. So you see, for example, if we choose this formula, which has a greater ppm for the parent accuracy, 2.9, then you see potential pieces that start to make sense for these 393 and 281. But as you say, if the parent doesn't have nitrogen in it, then this formula doesn't make sense because it has 6 nitrogens, which is an awful lot of nitrogens anyway.
I have a question. What if you go back to the main mass chromatogram where you have the isotopes, the isotopic peaks, and you would increase a little bit the what do you call it, the level. So the one you have a square around it.
On here?
Yes.
In here?
If you would increase a little bit that blue arrow.
So that, like that?
Yes, and then you would recalculate the formula from there.
Hang on a second, I gotta hide some things here because get the same result with roughly the same, definitely, I mean, that formula is really spot on. And the isotope pattern is really good. You see that? Well, it doesn't mean that it's wrong. Like I said, it just means that. So in MSMS, it happens in the gas phase, right? The collisions in the collision cell happen in the gas phase, and there are many strange configurations that can happen in the gas phase, which wouldn't happen that we would be familiar with in like organic chemistry and liquid chemistry. So you can get rearrangements, and you can get losses of things and gains of things that may not really make sense. So what we can do is we can go to the next step, be the structural elucidation, and we can see that. But as of now, we have a little bit of a puzzle that we are not able to match that data so we're not able to match the MSMS data, so these two main fragments, to any fragment pieces of this formula. That is our little bit of a dilemma now. Otherwise, everything else is pointing correctly to that formula. Unless this could this be a phospholipid and it has a phospholipid in it?
Well, maybe.
What did I type? PI?
You missed the CL.
Because I put the thank you. I put the cursor in between the C and the L. Thank you.
One more thing, why you didn't try to choose another dot, like the first one to the left, 6-0.
So you remember we set up our IDA to do MSMS 3 times. So this peak is massive. The first one is, see where the dot is? It's right here. So it caught the MSMS just on the upswing of the peak. So this is the MS. It's not so great. So I chose the last one because it's the highest up the peak I can go. I only did it 3 times, and then it turned off. Because I was not expecting such high peaks. So in my opinion, that's the best one. If you want to select this one, you can also, you can link the formula finder to whatever you want. So if you have labeled those peaks, you can change the link, and this is also a mass spectrum. So you can link it here, and you can see, get the same issue. So we have the same formula there, but you see the mass error is not so great because this is a really scratchy peak. You see even the data is not so good. See that? Because it's quite a small peak for the MS. We went from 8,000 to 3 million, right, over those 3 dots as we went up the peak. That's a little bit better.
إنه هو الأسامي مش حسب الإيميل عن كيف عطيتنا مش نحن عملنا نحن عملنا فيزيكس كيف نحن abbreviation هاي مظبوط نحن كمان
So what were we looking for?
If I'm not mistaken, if you click on PPM, it will rearrange them by order of which one is better.
Correct. It was a C53 though, right?
It doesn't exist anymore.
It was a negative.
But there is one that has a 0 PPM.
Did I click find any or did I click? I'm a little bit confused why all of a sudden we have so many hits. Why did we not have so many hits before for the same number? What is the difference? 4.5 to 1.9. See, there is a difference because of the intensity. That really makes a big difference. Looks like it does. So 2419 is 06 and 2445 is 20. Yeah, so it is a big shift. This may be too saturated and it's leading us astray. E6 may be too much. Even though that data looks great in terms of this fitting, may be that this is just too strong for the detector. And actually this is more reasonable. Let's try the second peak or the third dot. So if you're sure there's no nitrogens, we'll take nitrogen out.
Alek,
Yes, sir.
don't take my words for granted. I just did a quick dirty profile and I had a look, and I may be wrong with no nitrogens. Usually I would do what you're doing now, and then I would do NMR.
Mm. Well, we have a lot of candidates here, and that is the usual case when you have bigger compounds, because you have more probability of different combinations of atoms, right? So let's see.
Can we arrange them in the order of ppm?
We can, but keep in mind it goes to it goes minus. So then
we have to go for MS rank.
Yeah. Right. So I would say this is a candidate. This is a candidate. This is a candidate. This are starting maybe to need a restart of this computer. So these are the candidates here between 2 ppm. There's about 5 of them. What we can also do is you can limit the mass tolerance here. Say like 3. That'll make our life a little bit easier. And then we can link the MSMS and see.
The second one makes sense.
This one.
Yes.
Into O10. By MSMS, that comes, yeah, with 6 nitrogens is too many. Let's see the MSMS for this. Yeah, you see now we have candidates. So 41, 82, N2, O10. That's a lot of oxygens, though. Without a P, without a phosphate group.
Well, if you have amino acids and you have peptides,
So
don't base my words on the NMR.
Yeah.
Just see what you have here. But if you have a peptide with some alcohol groups, then you're fine. And you have a.
To me, this is not a peptide because there's only one main fragment.
Yeah,
so if this was a peptide, so you guys know, just for the other people, right? Because the other guys on the training, the peptide is made up of amino acid, and usually what happens is the mass spectrometer breaks the peptide bond, and so you have like a ladder, a beautiful sequence of all the peptide bonds breaking. So I wouldn't expect that there would just be one main fragment. That to me is, like you said, it's more like a lipid, and the backbone has broken and released, one of the fatty acids or something. So, okay. So what you would do now is you would try to take a structure for that formula. And usually what I turn to is ChemSpider, but there are many other different online databases that you can use. So if we just find the internet here, so ChemSpider is like a chemical encyclopedia. And we can search. What was the formula? Some notes going here. C41, 41, 82, and 202. So here's ChemSpider. To search, I don't know if you're familiar with ChemSpider. To search ChemSpider by molecular formula, it is better to go to intrinsic properties and to type in the molecular formula, because some people have entered their entries into ChemSpider with a, like, instead of CHNO, they've done CHON, and then it doesn't find it, unfortunately. So come here like this, and then you have your search.
Alek, we cannot see
Yes.
it.
You can't see?
No, the ChemSpider.
Oh, what happened? I think maybe we need to search the window, not search, or share, sorry. So share the whole screen is this one, right? Okay, can you see now?
Yes.
Okay, great. You're welcome. So unfortunately, there are no hits for that formula. I'm a little bit surprised how many oxygens there are, and also how many hydrogens there are. C41, there's like 2 hydrogens for each carbon. Yeah, it could be a long chain, I guess. But unfortunately, in ChemSpider, there are no structures. So the idea would be to find a structure or to build a structure, and to bring that into SCIEX OS. Do you have any idea of a structure or something similar?
Usually I've used the natural products database,
Okay.
dictionary of natural products, but we don't have the licenses. UV.
I see. Okay. In terms of the training purpose, so we need to get a mol file somehow. Let me see what I can do here. What can I do? What can I do? So we can try to make it with, let's say, 08. Just try, and then I'll add 2 oxygens. Where is my toolbar? Find. Doesn't give a name. (36,4) PC. It's phosphatidylcholine. Okay, let me try. that's 782. We'll try. $7.58. It'll do. Okay. So here is a formula. It's not 100% correct, but I need something to start in order to show you what to do. So the workflow would be, just to go back because that was a little bit disjointed, I realize. So here you have found a potential formula, and you've gone to the web or another source where you have a mol file. You can draw your own mol file, which I'm going to show you right now, but unfortunately you need some mol file to open. You can't start from nothing. So the nice thing about ChemSpider is you can save these pictures as mol files, and then we can bring it directly into the software. So you see it saved the mol file here. Now I can go to SCIEX OS and I can say File, Open Mol File. And then I'll find that, which should be in Downloads. Yeah, there it is. Okay. So here's the mol file, and now I have edit tools, so I can make it match the data that I have, and this will then allow you to do the structural elucidation. So if you highlight the whole thing, it'll tell you that it is 757. So we have to go to 763, right? So let's just play around. So this is neutral, by the way, 757. 757 minus 762 would be, so we have to remove 5. So what can we do? We can put a double bond on the end, right? So let's see here. Make like this double bond, and we can say set bond type. So for those of you familiar with ChemDraw, it's the same as ChemDraw. And then I think if we take this one away, we say set bond type, be single, and we do, maybe this will be correct. Set bond type, single. Now it is 759, so what do I need? I still need 3 more. So didn't I? It may not work because 3 is difficult, right? Which actually makes this fatty acid quite, this is a fatty acid, it makes it quite interesting. I can put, there's no more double bonds. If I remove this, I'm within 2. Set bond type single. So now I'm at 761. I got to go 1 Dalton more.
Yeah, you'll go H on the phosphate.
Yes. Whoops. Correct.
Because the nitrogen is positively charged.
But this is going to be, yeah, this is going to be, yeah, correct. Thank you. There we go, 762. So plus 1 will be 763. But it's not going to plus 1 because that's the charge. These things have a permanent positive charge.
Yeah, exactly.
Maybe that's what's throwing us off. Maybe here we have to make 0. Can't. Plus 1. Maybe that's what's throwing the software off, is because it tries to add a hydrogen. It doesn't know how to charge without adding a hydrogen. In the database, is there a way to do so? So in in peak view, sorry, in explore mode, it used to be called peak view. In explore mode, when you see this button with yellow and red, that's your settings. So you can come here and you can play with your settings, but there's no, let's see, we have M plus. It may not be smart enough. M plus K to M plus H. See, there's no M plus. Well, you've jumped off the deep end right here at the beginning. No problem there, but maybe some other people are confused. So we're just facing a few problems because you can see this has a permanent positive charge.
I think, Alex, you need to write the paper now and send it to publications.
Yeah. Well, I mean, we can work on that together. I would be honored to do that. Okay, so let's continue as if this will work. We'll just go a few more steps. If this doesn't work, perhaps what I would like to do is to return down the triazine track, because then I know it's kind of fake, but everything will work. So then I can show you really in the software the workflow. Because right now we face kind of a lot of problems, and we had a great discussion for sure, but we didn't kind of cover the workflow in a step-by-step way. Anyway, so we've opened the mol file, and now we need to link. So we can take the mol file and we can link it to the spectrum. See that? So we can do the same thing like we did with the formula finder and link it to the MSMS spectrum. And now you see you have a green arrow, so the green arrow shows you the parent. And the mol file is here. And now we need to open the last tool, which is the fragments pane. So under show, fragments pane is the tool for the in silico fragmentation. So we'll open that up, and then we get this extra pane here on the side. I'm going to just grab it. Make the structure a little bit smaller. Did I get it? Yes. Okay, and then we have the last linking to do. And this linking is to drag it to the structure. So you see, if you ever get confused about the linking, and I know that you will at the beginning because it's also not straightforward, just remember it's these little icons under the truck. And if you need to know what to link it to, just put your mouse over it and it will tell you what to do. Drag to a structure. So this is the structure, right? So we're going to drag to the structure. Okay, now everything is linked now. We have the fragments linked to the structure, and we have the structure linked to the MSMS. So we need to set up the fragmentation, and then we need to fragment. So this button here does the fragmentation. Here are the settings. So you have a lot of settings here, and you also need to kind of come here and familiarize yourself and play with them, and to see what you will allow and not allow. These are basically the rules on how the in silico fragmentation works. So usually what I do is I open it up a little bit wider than what the settings are here. So I say it can break up to 3 bonds total, and it can break up to 2 carbon-carbon bonds. Now, only break single bonds. It won't matter in this structure because we don't have any double bonds. But sometimes double bonds do break, so you do want to pay attention to that setting. Break ring bonds is allowed, so rings will open up. I allow bond closures. Brute force rearrangements are what I was talking about, like in the gas phase, how sometimes when we have fragmentation, then the molecule almost reconnect and rebond in a new way in the gas phase. So you can turn that on and off. You can also allow radicals, which means that you will have a fragmentation and breaking of the bond, but not reforming of the charge. So you can have a new charge almost generated from the actual break of the bond. Mass tolerance, so definitely we can change that, right? Because we are working with a high resolution instrument. So I'll put it to 15 ppm, and I will say use the peak list. Where is the peak list coming from? The peak list is coming from the your MSMS data. And then you have a minimum mass for fragments. Usually I don't really pay attention to that too much. If you check automatically recalculate on the fly, then any change that you make, it will automatically do the fragmentation. I wouldn't check that because sometimes it freezes the computer. So in this case, uncheck, you need to press the button, which is right here, to fragment each time. So don't worry, it remembers these settings for you, so it will keep them for next time. And then here goes the fragmentation. You see how long it takes? So if you do it on the fly, you have to wait for that every time. I don't really expect this to work. Yeah. Oh, actually, it did assign a 393. Okay, so basically what you have are you have two tables. One is the fragments table, and one is the peaks table. I tend to focus on the peaks table because the peaks table is the reading of this data. So we have only 3 peaks because only 3 peaks are labeled. You see that? We have here 394, 393, and 281. What it has told you is the percent intensity, and then it's given a check mark if it's able to assign it. And it's given the error here in Dalton. So you can click, for example, the fragment. It puts red arrows here to show you which fragment it's considering from the data. And now here in bold, it has shown you the corresponding fragment. Yeah, so this fragment 281 corresponds to that piece of the molecule. And if we look at 393, and it is this piece of the molecule. And 394 has
ميزان لتنك غاز.
It's in red. So any fragment that shows up in red has not been assigned. You have down at the bottom that you match 2 out of 3 peaks, which represents a total of 95%.
شكله الميزان مثل الميزانات اللي شفناهم وقت بسوق الخضرة وقت طلعنا على
So that's how the fragmentation
مثل شكله إنه شيء مظبوط.
Of course, this is a little bit tricky because there's really only 1, maybe 2 fragments. So the more fragments you have, and the more fragments that are able to match to the structure, then the more confident you are that it's correct. So obviously, as we've been discussing here from the beginning, this is, structure is a little bit difficult, and also this, let's say, phospholipid has a permanent positive charge, and that may also be throwing things out. We may have to do some things manually. I just want to see.
لأن حسيت إنك تعرفه بس هيك عم شوفه نسأل عنه بس.
So these are all of the possibilities.
كبير بالعمر.
Yeah, I was wondering what's going on. Did you see that? The error in Daltons? What is that? 10 Daltons? It's a mistake. That should be ppm. See? ppm is more reasonable. 10 Dalton error is huge, right? Let me write that down. I'm sure that was not like that in previous versions of the software.
لا بيبعتوا للهيدا وأنا بشوفهم بيرجعوا يبعتوا لي ماشي. الحمد لله. السلام عليكم. صار عمرنا 5 أشهر. لا أنت عازبه مش حالهم. صاروا 5 أشهر اليوم. إن شاء الله.
I'm okay.
Not you. Yeah. Everyone, what I would suggest that we do is just go through one example of the trizine. Of course, everything will work beautifully because they're trizines, and trizines are always
مش
perfect.
بياخد مصاري سؤال.
And then at least you can see the workflow as a complete picture of what you should do.
ماشي.
Do we agree that we should do that, or do you want to, is everyone okay, and do you want to go and talk about it in the analytics?
You can have a go at the triazines. It's quick.
Yeah, it's quick. My gut feeling is that some people are being quiet because here they are quite confused.
Yeah, maybe go for the triazines.
All right, let's do that. Okay. So unfortunately, there's no way to say explore mode. So I'll just leave this one open in the back because I have a feeling that maybe this is a good start for you, Tony, and you want to come and play with this at a later time.
We'll be there in about 10 minutes.
Yeah. Okay. So I'll leave this here. So what we'll do is, all right. So just to go back to someone else's question who asked how to open the files. So yes, from the queue, we can double click. That's one way to get to explore mode. You can also enter explore mode and you can say file open. That essentially does the same thing. Or if you find something in analytics, you can use this button. Those are the three ways to get to manual explore mode. So what I'll do is I will open a data file, but now I'm in the wrong project, right? So we need to say browse. And we are in training data. So let's open a B IDA from last night. All right. So we'll open it as a standard TIC, and we'll do the same thing like we did with Tony. But what we'll do is I will show you the XICs. And we'll choose one of the XICs to work with. All right, so let's choose this one. So we'll double click. We have our target, and we have our mass spectrum. I didn't double click. Okay, I'll double click. So the mass is the 228 right here, right? So what I'll do is I'll zoom in for that. And then once I have, this is good because it has a chlorine, right? You can't see that. No, the 230 is another compound, right? Okay, forget that. So as you can see, the mass is here, and when I have the mass spectrum that I want to process open, I will go to show formula finder. That's the first step. Show formula finder. Now it starts to get kind of busy, so I use the truck to align things correctly, and then I start hiding things that I don't need at the moment. Okay, so to link the formula finder to the data, we use the MS linking button and release, and then it highlights the region of the spectrum we want to process, like that, and comes to, yeah, now I selected it, it's choosing the ion type correctly, and we can say find And we don't have any, probably our isotope density tolerance is off. Well, so now I'm stumped. Why is it not finding a formula for that? Because I know that the mass is perfect. Did I change something to zero charge state? No, I kept this at +1. Didn't change any settings. Somebody catch a mistake I did? Carbon, hydrogen, nitrogen, oxygen, sulfur.
Normally, you shouldn't think an MS spectrum also.
Yeah, that correct. That would be like the second step. So it should work just from linking the MS. No elemental composition we found. Formula finder studies need to be adjusted. No. What am I doing wrong? How come it works with complicated things and not? That's such a big mass error. We never saw that. It's impossible. All right, give me a second here. I got to work out what's going on. This is sample 16. It's the F2 CEB. This is F2 CEB. This one, right? And 228 is Amitrian. We have 0.4. Yeah. Oh, it has 5 nitrogens. Do I not? Maybe I don't have enough nitrogens. That's my mistake. No, I have 10 nitrogens, 5 sulfurs, carbon, hydrogen, nitrogen 10. H17 and 5S. Yeah, boy, what's wrong? It's the data is perfect. Did I change something else? Well, the only thing I could suggest is maybe we had too many error messages before, and we should make a restart. Plus uncharged, correct? This is an MH plus. Number of carbons over hetero atoms. So we have, these are not weird compounds. There's 9 carbons over 6, so 9 over 6 is still more than 1. Am I missing something very obvious? Not that I can see. Try to link one more time. Doesn't make any sense. Let's just look for another. Look at another one and see if it's something to do with this mass or if it's something to do with the software again. So the red is 226 here. I have sulfur there, right? Yes. 19N50. So 226, 1665, 226. All right, it works for this. Why did it work for Ametrium? We have still 6 heteroatoms 10. 10 divided by 6 is still more than 1. Okay.
Of House Targaryen, of the blood of old Valyria, I am the dragon's daughter. I am Daenerys Stormborn.
Maybe that's off the carbon isotope.
Of the blood of old.
It's weird. All right, I have to look into that after if I can understand why it won't find that one. As you can see, it finds it in the analytics perfectly. Type sulfur. All right. I don't know what's going on there, guys. I meant to show you a simple example. So we'll focus on simazine instead of ametrium. All right, so here's the mass peak. Highlight it so that it shows up here. Make sure that it's linked. And make sure you have the ion type. Press find. And that is exactly the kind of results that we expect, less than 2 ppm. So now you have your potential formula. Of course, in this case, it's simple. There's just one, because this is a little bit smaller mass. As you saw from the other compound we did, Tony's lipid there, whatever, there's a lot more formulas to go through, and that is normal. You'll have to go through them one by one and proceed and look at the MS&S and see what's correct. So the next step, what I would do is to find the MS&S. So we know how to do that using the IDA Explorer. So from the IDA Explorer, we can look for mass 226 as the parent at retention time just before 7 minutes. So I'll say show IDA Explorer. Here's the dot plot of the sample, and we're looking for 226. Which will be right in here at retention time just before 7 minutes. So here we are, 226, 1664. There we go. So there's the MSMS, and you have the same 3 choices because we set up our IDA methods for 3 MSMS of the same thing. So you choose the one you want, perhaps the one that's the most intense, and then you can link the MSMS spectra you found with the second linking button, like so, and I'm going to find again. Now you have PPM for the MS, and now you for the MS and for the MSMS. Okay, so you can click. Let me move this over here. A little bit more room. All right. So now you have this this plot of different colored dots. So what does this represent? This is taking the MSMS spectrum, and you have it here basically as each peak is one set of colored dots on the x-axis, which is mass. Y-axis becomes ppm mass accuracy. If this formula, C10H19N50, if that formula matches the 226, the parent, then each one of these daughter ions has to be a piece of this formula. We don't know how it's put together, but it has to be a piece of that. So what the software has done is it has taken all of the peaks that are labeled above the threshold, and it has fed them into this system and tried to map a piece of the formula. So I lost audio. Okay, the audio went out for a minute, but it's back. All right, and so it tries to match a piece of this formula, C10H19N50, a smaller piece with these masses, and then it plots them for you on the mass accuracy scale. So what you are looking for to confirm at this point that the formula is at least okay is that you have dots that are close to 0. So again, the mass accuracy is roughly around 2, right? So anything greater than 2 would really not be a candidate as a potential fragment. So in this case, it's relatively okay. You see that some of the fragments do match. Some of the other fragments here don't have a potential formula, so it was not able to match a piece of this formula to these fragments. Now, in this case, we know that it works, right? We know this is so this is somehow, let's say, roughly a confirmatory result. So what you would do at this point is that, like this formula, you would go to a database and get a mol file. You can use the ChemSpider like I showed you, or you can use another source. So we'll just take that C10H19N50, and we'll go to ChemSpider. And we'll say advanced, and like I showed you before, intrinsic properties, C10H19N50, and we'll search that. There we go. So these are all the possible candidates that match this formula. So the first one, that is the pesticide, and you can usually tell if it's something known because it has also a lot of hits and so on. So I think what we'll do to show you sort of how it's working is we'll take the pesticide and we'll take some other structure that's clearly not correct. perhaps this one here, or maybe this one here with the long arm, or this guy here with the long fatty acid chain. So you get a feel for how the structural elucidation is working. So let's do this one first. And this is how it works. You have to check each one of your candidates. So you get the formula, save it as a vol file. Now we go back to the OS, and we can open the mol file in the OS. So here's the mol file. And once we have the mol file, we use the linking, link it to the MSMS, get the green arrows to identify the parent. And now you can proceed. The last thing to open is the fragments pane. Fragments pane opens here on the side. A little bigger. And then you need to link fragments pane with the structure. Once you do that, you can go ahead and fragment, and you can see which fragments have been matched are in blue and which fragments have not been matched are in red. That kind of makes sense because these two also, oh no, 184 was able to do here, but it was not able to do 142. So red fragments have no match at this point. And you can go to peaks and you can click, and it highlights here in red and it shows you in the bold color the correct piece. So that is interesting. 184 and 142, two big diagnostic fragments, no match. So that probably means that this structure is not correct. The smaller pieces match, which kind of makes sense, right? In MSMS, the smaller pieces are common to a lot more parents. So smaller pieces may match in a wrong match, whereas bigger pieces are more diagnostic. Okay, so this was clearly not the right compound. I'll keep it open there, and then what you can do is you can go and open another structure, let's say, right one this time, save, or 759, and I'll open that mol file as well. All right, I'll just put those all on the same line. Okay. So with multiple things open, you can link to multiple structures. So I'll link this, I'll link the fragments to this structure now, and I'll link this structure to this MSMS. All right, and then I'll hit fragment, and then now you can see, aha, the difference, right? The two big fragments now. Much more diagnostic fragments match, and I can confirm it here, click, and I can see, okay, it makes sense, it's that piece of the compound, which obviously wasn't present in the other structure. So, all right, so that was my goal, was to show you an example that worked all the way through, so that you can see the workflow. Again, this is all written down in that PDF guide. So it also takes you step by step and takes you through the linking and so on. So any questions on this part? And let's not focus too much on how we find the peaks. We get to that when we go to analytics. But the part after that, once you have the mass spectrum, formula finder, and finding the MSMS, and doing the structure and the fragments. Everybody totally lost?
We're with you, Alek.
You're with me. Okay,
Yeah.
great.
Could we possibly now try to go to the analytics and try to decipher the compound of Tony from there?
Absolutely, yeah, we'll do that. Yes, that's the next step. All right, so I will also leave this open. So you have one example here that's open. Okay, so in the analytics, you have the same way that we always start, results. And now what we'll do is we'll move just a few of the data over because the non-target processing takes a long time. So, Tony, just remind me, what was your sample again?
I believe Tony has left us. Basil, one of the students, is here with us.
Okay.
Maybe Basil
Right.
can
I
let
can
us know.
I can find the answer. It is ZK322F2CEB. Now I have to remember that. All right, so okay, so ZK3F22CEB. So that's the spike, and that's the non-spike. All right, great. So what we'll do is we'll process it two different ways. We'll process it one way where we use the A as the blank, and then we'll process it another way where we don't assign any blank. And then that way you guys can see the difference in that processing. Okay, so at this point we don't have a non-targeted screening method, so we need to click New. We want to make one. And this is going to be a little bit easy. I'm going to uncheck and uncheck and check on-target screen. And you see when I do that, I lose my compounds and I lose my integration. And why is that? It's because the software is going to find that for us. It's going to find anything that has a peak shape. And like I was mentioning in the previous discussion with Tony, I hope that was clear to everyone. What is the most basic, let's say, feature of how a compound behaves in the LCMS system? The most basic feature is that it has to chromatograph. It has to form a Gaussian peak shape off the LC column. If your compound doesn't do that, you pretty much won't be able to identify it. If it forms like a smear or it doesn't show up at all, then we won't see it. If it does form a bad peak shape, you have a chance to find it, but it will be a little bit more complicated, at least using this automated way. So that's why we don't have components or integration. Library search is probably a shot in the dark. So, for example, so library search is probably a shot in the dark that you're going to identify something that's in the library, but it doesn't hurt. So turn it on. Now we don't have any names, right? Because we have no components. So candidate search. We're doing IDA. So purity is okay. Search all the libraries. Why not? I will turn collision energies off. And I will put here for the precursor, I think I put 0.05, right? And here I put 0.05. Okay, so that'll search the library from the data we identify, and perhaps we'll see something. Of course, it's going to find the triazines because they're in the library. So we may come back and do it again without the library search, just so that I can show you how to identify those. Or we'll try to maybe just ignore the library search data at the beginning. Calculated columns, again, not for us right now. Wait a second, I've got a cough here. sorry about that, just a little bit too much talking. Okay, so calculated columns, we won't have, come back to that if we do quantitation in the future. Lagging rules, you see, well, again, those are all turned off now automatically because we have no components or integration, so we can't do quantitation. Qualitative rules will turn it on just to see the library hit score, and also we'll use formula finder as well. So those scores are okay. We'll put here 50 and 50. So our combined score will be a mix of both of those. All of the other parameters are only applicable if we give a target. And here we give no target. So there's nothing to calculate EBMS error against, for example. Formula finder, so this is the same program, but we just used it manually, but now it's going to be automatic. We need to turn it on. And then you have a choice. You can use this radio buttons if you want. You see that when you do that, it alters the elements. Or you can type it manually. So I don't want all those other elements there. So I'll do 100 carbons and nitrogen's fine. And then what I'll do is I'll add chlorine and I'll add phosphate. Okay, and then phosphate. And then I will keep the mass tolerance 5 ppm. So you're controlling here the limits of the formulas that you will find. So again, if you're expecting to find something, somebody mentioned they're looking at compounds that contain metals and so on, then you need to add the metal in here that you're expecting to find. And the reason we do that is only for computer processing. So if you have the whole periodic table here, it'll just take forever, the processing. So do adjust that based upon what you expect to find in your samples. And then the last setting is the non-targeted peaks, which is probably the most important. So we have the first part of the settings are to cut the retention time. So for example, we can remove the end of the run, and we can remove the beginning of the run. So what I'll do is I'll say, okay, so like for the first 0.8 minutes, it will not use, and maybe the maximum retention time, we can do something like after 16 minutes, it will not look for compounds. So that cuts down your retention time to where you may expect to find your compounds in your gradient. Now you don't have to use that if you don't want. You can turn it off and leave it on 0. But you'll find that you'll get a lot of really ugly peaks early and late, which may just cloud your analysis. And you'll have a lot of things you'll have to filter through. Okay, so now you have a slider bar, and this slider bar is basically how thorough the algorithm is in finding a peak. So we don't have any specific settings, number settings, or so on. But if you put the slider bar here, you'll have the fast processing, but it's not going to find really any smaller peaks or any peaks with a little bit of abnormal shape. Everything has to be perfect. And then over here, it's really going to find so many peaks, even very small ones and ones without a good shape. So normally, I kind of leave it on either the second or the third setting. But that is definitely something that you'll have to come and play with, and depends on how good your chromatography is. As you see today, we have pretty good chromatography. In my opinion, a few more data points would be good, and then we would have really good peak shape. So here, the next setting is the area ratio threshold, and this is how much bigger the unknown sample must be over the control. This is where you do choose a control, a blank, and usually I put something around 5 times. So the sample, the peak must be 5 times bigger in the unknown versus the control. And like we already discussed, and we had a big discussion about that actually, whether it's useful to use a control or not. So that's up to you guys. I think at this point you understand the plus and minus. And like I said, we're going to do this twice. We'll do it once with the control and once without, so you can see the difference. And the last setting then is to group the peaks that are found by adduct or charge. So it means that if it finds an MH plus and a sodium adduct and an ammonium adduct for the same compound, it'll group those together. They won't show up as 3 separate hits. So that's useful, that you're not then somehow finding the same thing 3 times. So it'll be clearly identified that those addicts are together. All right, so that's our processing method. I will save as, so here, say non-target screen with control, and I'll say 5x because we set the control to be 5x. We set the known to be 5x bigger than the control. Okay, so save, and then we'll say, last thing we'll do is step 3, which was not available before. This is available only for non-targeted workflow, is that we select the comparison sample. So what you are doing here is you are selecting the blank, or the thing that will be the control. So in this case, that'll be sample A. And B will be the one that we try to identify compounds in. Okay, so let's say process. You see it's going to take a little bit longer than the other kind of processing. Okay, so as usual, minimized itself. All right, so this is our big chart of all the things that it found. And so we have potentially, let's see here, have potentially 380 items or compounds that it's found. So what I'll do first, like always, is I will adjust my columns to match. So I think the first thing I might do is apply the library column, and then I'll come in and I'll edit this. And there's a few interesting columns we'd like to add. So the first one is area ratio of comparison. That is how big the area is with the sample divided by the control. So that's a very useful, if you are using the control, a very useful column to show, because we can quickly order the chart by which peaks were the biggest relative to the control. Combined score is okay. We don't have an expected retention time. We don't have a formula. Formula confidence now we have. Formula finder results we have. And formula finder score. Bound at mass is not is used. Yes. Okay. Index fragments we're not using. Height ratio. Let's see. So isotope we don't have anymore. Library we have. Mass error. Mass error is not reported because we don't have a formula yet. All right, precursor mass is okay. Non-targeted peak, have that. Sample type. RT confidence we don't have. Retention time, okay. All right, so I'll say okay. Now it'll get a little bit smaller, and then what I'll do is I'll go back and I will export these settings in the same place as the other one, which is inside SCIEX. So then I will say this is non-target screen library search. now, when you do this again, that will also populate in this recent table settings. Yeah, you see now you have both there. Okay, so also be sure that when you do this, that you are actually looking in the sample and not in the control, because both will be open here. You can see which one is marked as control because it has the C next to it. So what I do is I start by taking area ratio of control and I sort the chart by that. So now what comes to the top are the compounds, or let's say the peaks, that have a much bigger area ratio versus the control, the standard. And then I can do the peak review. Yeah, see, so you have these things to wade through here. Let me make this a little bit bigger so you can see it. And I'll scroll to the top. And I'll go through. So this is a problem that happens because the slider bar in the method is not in the right place. So it has integrated this as a peak, which I think we all agree is not a peak, and it's proposed that to you as a possible target. So what you could do is you could also show signal to noise as a column, and then you can see, okay, this doesn't really have great signal to noise versus how big its area ratio of control is. So we just, at this point, I just ignore these kind of things. It may be more interesting to move that slider bar for this sample more to the left side. Try to ignore that kind of thing. So this is definitely interesting. This is something that's in the spike, which is not in the real sample at 537, and that's not one of the triazine compounds, right? So, but you see that's a definite candidate to follow up. There's a nice peak in the sample. Okay, it's a split peak, but that could be because it's an isomer or something, right? And there's no peak here in the blank. You have the MS, and you have the MSMS. And so down here you have the best formula, so the formula finder results and the error. And here's the MSMS error, 2.4. Now I didn't find anything in the library, so this compound is not in the library, but it has a potential formula. So at this point it would be, so this part of the software has accomplished the peak finding for you. So now you have this as a potential target to continue in the manual mode what we did with the formula finding and the structure. So now you need to find the structure for that formula and go to the manual mode and start with the chem spider and the structural elucidation. So don't forget you have this button to do that, right? So you can go directly to Data Explorer from here. So the analytics is helping you to find potential targets versus the blank, right? And look at this peak. This is E5. Okay, let's press the button, and I'll go there and I'll show you what I mean that you won't see this in the TIC, right? So here we went to the Manual Explorer mode. That's the XIC. This is the mass spectrum. This is the MSMS. All right, so I'm just going to show you. There's the XIC. That's quite nice. Now we go show TIC. And I'll just choose the top MS. Right? So this is not visible in the TIC as such a clear peak, 15.5 and 15.8. Yeah, so maybe it could be those two, but this is E5 and this is E7. So if you look, if I zoom out in the mass spectrum, what was the mass? I zoomed out too quick, I didn't look. 537. Okay, so it is quite a clear peak there. So this one is borderline. This one you would perhaps be able to identify if you just went to the TIC and you searched around a little bit. Maybe after a little bit of time, you would be able to find it. So this, I would say, either approach would work. There's the parent that you're interested in. So we don't need to go through the manual way again, right? Everybody understands from this point onwards, you would go to formula finder and fragments, structure, and so on. So let's go back to the analytics and keep going. So here is the other side of that peak. Okay, that makes sense. And then 226. So there is our one of the triazines. That's interesting. That is a 593, which follows the same retention time pattern with the split peaks as that 537 stuff. So those could be possibly linked together with maybe that's an adduct or a fragmentation. 589. Yeah, so that's probably rubbish, right? Not really a great peak that we can really say, okay, that's a compound. That's one of the triazines, probably. Yeah. Again, 577. So there's a couple things with mass around 500 which are present only in the spike. Maybe if we chase that, it ends up being some plasticizer or something that has perhaps been added along with the pesticide or a stabilizer. There's the triazine, and that's the two of them. That's the promutrin and the terbutrin. Yeah. Again, not a great match, even though the mass spectrum is quite nice. Great match. Yeah, that's a lot higher in the sample, even though it's present here, present in the blank. It's a lot higher in the sample. 291. What does it say? Trimethylprim. That's a pretty good match too. Look at that. Maybe that's also in the. That could be possibly in the triazine mix, and they don't tell us because that is a. Isn't that a pesticide? Trimethylprim. What's trimethylprim? Antibiotic. You have trimethylprim in your bacterial culture. Yes, maybe. Anyway, we've identified that pretty nicely. All right, keep going. Yeah, so again, not a real peak, right? Yeah, not a real peak. And that's a difference. That's the same thing, but it's just integrated not exactly correctly. So the data, again, with better data points, the peaks will be better defined, and it will not make those kind of mistakes. But here the integration is cut there, and then here it's continued over. So it thinks the area is greatly different. And then after that, probably things are going to drop off pretty quickly. Yeah. Which they should, because the samples are identical. So see this kind of problem, right? Where the peaks are not in good shape, faces a problem. It doesn't exactly know how to do it. When the peaks are in good shape, with enough data points, it's clear that it can work nicely. But with this kind of shape, it faces problems. That's why the chromatography is so important, this unknown analysis. All right, my voice just barely hanging on after a whole week of talking. Okay, so I think at this point you get the idea of with the control. So now let's try it without the control. So obviously we didn't find that compound that Tony was working on in this way, because that compound is the same in both of the samples, right? The only difference is the triazine mix and maybe trimethoprim and maybe some plasticizers that got introduced along with the triazine mix. So let's run it again, and now this time we will not choose control. We will just process, and we will say, okay, find peaks. Maybe we'll move that slider bar a little bit more to the left, and we'll see how we do. So that'll be the next step. But let me just pause here and ask if anyone has any questions. Also drink some water. All right, I'll take that as a no. Everyone understands. Okay, so we'll come to results and we'll say new. Oh, I'm not watching the chat. Actually, are people writing in the chat? Nobody left, actually. Nobody chatted. Okay, the ZK3 sample. Okay. All right, so what we'll do is we'll take those two samples again and we'll move them over to the right side. So ZK3, CE, A, and B over. And now we will, so what we can do, well, let's browse in the method we already made. So we don't have to do so much clicking. And then we'll say edit, and we'll just change a few things. So library search, we'll leave it alone. Flagging rules, we'll leave it alone. Formula finder, we will also leave it alone. And the changes we'll make are in the non-targeted peaks. So let's move this over one. Let's try to make this a little bit bigger. And does anyone remember the retention time of Tony's stuff? Unfortunately, we cannot go look. It was 15 minutes, wasn't it? So we can't go much shorter. All right, we'll leave it at 60 minutes. 14.5. Okay, thank you. So yeah, we can't go too much. We can't go too much lower. We'll leave it at 16, and we'll put the area ratio of control to 0. And so now what we'll do is we'll say save as, and I'll just choose the non-target screen, and I'll make this, and I'll say no control, right? No control. No control. All right, save. And then here we will not select something. Process these as individual samples. All right, so here we go. So finding the peaks first. Minimized. Okay, so now we have the chart where we have just found peaks. So the first thing I'll do, as always, is apply my table settings, and I will come to non-target with library search. And what I'm actually going to do is I'll add signal to noise. So I'll say more, table display settings, and we'll find signal to noise. Is right here. Yep, signal to noise. Okay. So now we have the signal to noise here in our chart as well. What I might do, I just might write, that's kind of important, right? So what I'll do is I'll say export, and I'll add that to the non-target settings. Non-target screen with library search. Save. Yes. Okay. All right, so we have a couple different ways that you can sort the table. Of course, you could look first and see what you have as a library hit, right? That could be interesting because that's kind of your shot at the dark if you identified something from the library. Oh, actually, I don't think we talked about that. If there's no funnel for the colored icons, yet there's no funnel to filter, but you have this thing here to filter. So you could say, okay, for library, I only want to see there are my green hits. That's interesting. It didn't find the triazines. Maybe there's A, yeah, B. Even in B, it didn't find the triazines. Interesting. All right. Okay, so now we're back looking at everything. All right, so you can pull up, of course, the peak review and start looking through it. As you can see, you have a nice peak there. Okay, it just so happens that index 1 is the trimethylgroup, so that was identified. So again, this part of the software finds for you the peaks, and it presents for you the mass, and it starts the formula finding. So here's your formula. Here's your formula for this peak, and here's your mass error. So then, in my opinion, the next step would be that you go to this button and you go to Manual Explorer and you start doing your structural elucidation work. So as you go through the data, so we see the peaks. So I think you start to get an idea. Okay, there are just so many peaks of these samples. That's why when we match to control, all of the things that were different came to the top very easily. Whereas here, you have a zillion possibilities of things that look nice, right? This meets our criteria. This is a beautiful peak shape. Here you have a nice mass, you have a nice formula, great mass error, right? And good MSMS. So what is this? You have to take this now to the structural elucidation and continue. And you've got to do that with each one of these. So if you can somehow simplify this data set, it might be at the end that this is some, this is some amino acid or something that is present in bacteria culture anyway. So unfortunately, at this point, we don't know. We have to go and identify it. So that's why I'm saying that if you can make this control, which is the difference, then it will exclude the things that are the same. And as you saw, we didn't find this. All right. So what we can do is we can also sort the columns by signal to noise. So we can take the peak with the best signal to noise. So that's hopefully going to be the best peak shape. And this is his stuff, right? Yep, exactly there. So actually, cool. I was not expecting that. It's better than my expectation. Okay, cool. That's good for you guys. Look, there's the peak, 14.5 minutes. 739 was the mass we were looking at, right? And there's the MSMS spectra with just the one peak. But take a look. There's also many, many other candidates here, right? Each one also looking possibly interesting. Here's the 763. Oh, actually, it was 763, right? That we looked at, 739 or 763. But we said there's a couple different at the same retention time. There's a couple different masses that are similar, all in that 700 ballpark. So I guess it depends on your own philosophy, which way you like better. If you like to go into the manual mode directly and try to find something, or if you like to make this list and go through the list. The list may be a little bit easier because you can sort by these different categories, and then as you saw, actually interesting things did come to the top. Let's see, just curious, why in the B file you didn't find the triazines. Let's sort by precursor mass, smallest to largest, and then, wow, so no 202, no 228, no 226, no 242. So the algorithm had many other, let's say, bigger peaks and more interesting things, and it did not find the triazines in this sample when it was not using the comparison. So that maybe is telling you something, because the triazines were in the E4 to E5 range. But here they are not found in the target list. So we're only able to find the triazines with control versus the on-spike. Just look at the spike by itself. With this method, we didn't find the triazines. That's a little bit below my expectation, but okay, possibly.
Could it be due to the slider setting?
Yeah.
Exhausted.
Yeah, exactly. Yeah. Run it again. Yes. I agree. 100%. So where was that? So what's this for? Takes a little bit longer because the list is going to be long. Is it frozen? Or is it just thinking? Not frozen. Maybe we are now pushing the limits in terms of we didn't restart the computer and the memory maybe getting a little bit full, and then we ask it to do a big task here. This is also another reason why it's a good idea you have your extra license to set up a processing station, so that if this does happen, it doesn't interfere with the running samples.
Maybe if you use the for the exhausted but not the maximum, a little bit less. One
Yeah.
point.
Maybe
One more question I
yes.
have. Meanwhile, is that we have a license for the Cam Spider actually connection. So it was not set up. Yeah, this is, but it was not set up by Murray. Just beyond the scope.
Well, to be fair to him, the Cam Spider is for 1 year, so probably he doesn't do it because he doesn't want to waste your any time. So that's something we can do it. Well, I haven't done that in a while. I got to think, how do I do that? Where does it go? So basically, you can get the license yourself, I think, right? Because you do that through SCIEX, you do that through the web page.
Yes.
But then I will show you where. But the easiest thing is that there is a button to click. Now I remember. Yeah, there is a button to click, and you can click this button, and then it will put the library for you automatically. But here. Stalled. Have a look what's going on. Yeah, see, look how much memory it's using. it's not using the processor, so it's not really doing anything. It does really look like it kind of stalled.
So is it safe for us to kill the process this moment, or for the software, is it safe to do that?
Yeah, it's safe. It's not going to, you just lose anything that we didn't save, right? That's all. And in Explore mode, nothing is saved. Wish they had like a cancel button. What we can do is to try this. Please use the cancel button. Yeah, but there's no cancel button anymore. These guys have a good sense of humor, huh?
Recover better. Stand up for human rights. While the 2020 Human Rights Report is still not issued, you can read reports from previous years by swiping up.
Yeah, it seems to be stuck, right? Because it's not doing anything.
Human rights and labor on social media.
All right, how much else we can do? Try to close everything. Yeah, well. If there was a cancel button, we'd use it. All right. Okay, we did it. So what I will do in that case is I'll just restart the service. So the service for SCIEX OS is called Clear Core 2. Clear Core 2, that's the service for OS. And I'll just hit restart. Yeah, I see something was stalled because usually that goes quite fast.
Payments. You can read.
All right, let's give it a try. We may have to restart.
You can. Payments. I just finished. كان عصبت لكم فيديو عن موضوع الكيتو دايت. بدكم تشوفوه بكره ان شاء الله.
Give it a shot, and we'll do it without slider bar quite so far over. Oh. And this simple, right? And we'll say browse, and we'll grab that one, no control, and then we'll edit our target piece. All right. Oh, because I did it from within the method, right? It didn't do it from
This is the first ever SUV from Aston Martin.
See if that works.
It's beautiful top part of the glass, and then
Find
you
the
flip it,
peaks.
James Bond style. Ready?
And it got stuck when it went to integration.
This comes out, and this
It's right
actually
here.
turns into a key fob. Now, if you want your real
There it
James
goes.
Bond gadget, watch
It works
this.
this time.
Boom! There you go. Little bit of
And I'll show you the
movement.
button for the Chem Spider also right here. Let me look at this data.
Check out these rings. Love the pattern of these rings. Never seen that before. My car. A whole door panel. Head on around the back, guys. The other thing I love, one panel of glass the whole way across the top. Everything in here is made of leather, even the handles. Above that, stitching, everything's beautiful. You've got leather over the speakers, not steel or chrome. Alright, let's go. Holy moly! That is much faster than I was expecting.
Here we go. So let's bring my table settings first. Recent table settings, non-target screen. Alright, and then we'll have a look at the B sample, which is the spiked. And I guess we can sort by signal to noise. Yeah, there they are now. Still quite far down. Lots of good candidates. So you do have a button that takes you directly to Chem Spider. It's one of these buttons. Yeah, start a Chem Spider session. So basically what that will do is it will open not licensed. So you need to say yes, install the license, and then just follow the instructions. So put your license key here from the package, and then go to this website. One of you, I guess, is registered as the instrument owner, and you'll get the license by email and then install the license file. You have the AID code.
Okay, we'll do that.
Do it. Okay.
Do it right now.
It's not necessary. Just basically what will happen is two things will happen. One is your 1 year will start. And second thing is after you click that button, you will get basically a page that looks like I just do a manual. So we lost our data now, of course. So if I just show you, so you will get a page which I'll just grab some data here. Yeah, okay, fine. So then you will have show, oh, I have to open the mol file first, show you what it looks like. So you will have your mol file, and you will have fragments. So it will look like this. You'll have, and you won't have to link anything, it's all automatic. So over here you'll have your structure from ChemSpider. Here you have the fragment screen. Here you have the MSMS that you've selected. And here it's different. Here you will have all the hits automatically from ChemSpider. So you'll be able to click on the different hits from ChemSpider, and you'll see the corresponding mol file directly here. And then you'll be able to do this part the same, fragments analysis and the spectrum. Anyway, if you run into trouble, of course, I can help you next week. So that will come as a separate window after you press that button. And the MS information, the MSMS information is here. So we'll use that spectrum. And the formula it will use is the formula from here. So you don't have any control over that. So it's like automatic ChemSpider on this data that you're looking at right now. I'm pretty sure you will instantly understand.
Sorry, I don't know if I'm the only one who is not seeing your screen what we're talking about. For the spider, the ChemSpider, I'm seeing just the analytics.
Yes, that's all we're looking at. We're just talking about how this button will work. So
talking, not sharing anything.
No, yeah, because they didn't install the license yet. So I'm explaining what it will look like once the license is installed, and then I showed this in Explorer. Did you see this? So
yeah.
The new window will look something like this. Yeah, but in this upper left, you will have all the ChemSpider things. Unfortunately, I can't make it work without the license. But I'm pretty sure once you do the license, you will instantly understand because you know what these three panes do. And this pane up here is just ChemSpider. So anyway, try the license and see what you do. And I don't disappear after today. So if you run into problems, we'll get in touch and we'll answer your questions and fix those problems. All right, so this was our non-targeted screen without the control. So you see we do have a lot of nice, interesting peaks. Here's the 700 stuff, so that does show up. Okay, that's pretty good. And then where is the first triazine that we added is, and how did I sort this? I sorted by signal to noise, yeah. So in terms of peak signal to noise, so this column I sorted. The first triazine, which is what we added, is there. So what's that after about 30 hits? Ah, interesting, it does the split one first. There we go. All right, so that's kind of it for the non-targeted screen. So we went through two ways how to do it. One way manual, and we did give, I guess, a little bit sidetracked there because we started going and looking at the lipids and stuff. And then the second way is through the analytics. Like I said, if you want to use the analytics, it works pretty good here without a control. But as you saw, when you have the control, those triazines come right to the top as the difference. So if you can have the control, that will help you a lot. So anybody have any questions? So maybe we make a little bit of a plan for next week. I have Wednesday and Thursday available if you would like to continue on those days. I don't really have anything more to show. Oh, what I wanted to ask you is, do you have any other software? Because we did discuss, I think, at some point, like Metabolite Pilot and Marker View and stuff.
What do you mean exactly, Alek, by other software? We only have this one, I guess.
Only this one. Okay, fine. All right, that's fine. What I suggest we do, maybe we just take the rest of the time, or I don't know, 20 minutes or so.
So,
and,
yeah, you're not available on Monday and Tuesday. Is that correct?
Correct. Yes.
All right. So Wednesday and Thursday you're available all day, like from 9:30 till 4:30 with a break in the middle.
Exactly. Yes.
All right. So I guess maybe we can try to run some other samples tomorrow with a different research group.
Right.
Exactly. And perhaps we'll try to process the data for those next week with you.
Yeah, I would. So what I would. So I don't have any more like. There's no more program like to show, right? I kind of covered everything. Even though we did that in a basic way. So yeah, I think that's a great idea. Maybe we just discuss together. I mean, of course, you can run whatever samples you want, but can discuss together a little bit of a plan of what samples would be good to run to test your abilities in the software.
Yeah, and perhaps also you can share with us some of your tips about what tweaks can we do perhaps on the method development end.
Well, yes, that's a good net. So in terms of the MS, as you can see, I think we are getting pretty decent sensitivity right now. So there's not a lot I would do in the MS methods. But what I would like to do for the LC method is to, let's say, make the chromatography worse. Because right now we have a little bit, the chromatography is a little bit too good. Our peaks are a little bit too narrow. So what I would like to try is a 400 microliter per minute method. And that will reduce the flow. Yeah, obviously reduce the flow. It'll reduce the pressure, and then with a lower pressure, we should get a little bit wider peaks, and then hopefully we'll get a few more data points. So we can control the flow right here. I'll just put 0.4, and then we have to do that for each step of the gradient too. So you guys can test this method tomorrow or Monday, Tuesday. And then save as. And so I'll keep the same, but I'll put 400. So I think that'll be a little bit better for giving us some more time and some more data points across the week. Like you see, there's nothing really wrong at the moment, nothing drastically wrong, even minor wrong. The data points is really minor because we're able to identify everything nicely. So, like I said from the beginning, this instrument is not about method development. Don't get caught in that track that, oh, I need to work on my method or something to make it better. As you can see, the method is very sensitive, and we have a wide range of coverage over a very nice gradient. There's nothing here that we didn't detect, for example. So I think, especially at the beginning, all of your efforts should be on data processing and really learning the software tools 100%. So that's what I would do. I would have that other LC method, and you can experiment with that. In terms of the MS method, the two big things that you would change would be the mass range, right? So right now we are measuring from 200 to 1600. So we want to, basically the rule is you want to have the smallest mass range that meets your needs. So if you, for example, are looking at no compounds below 300, then change the mass range to 300. If you're looking no compounds above 1,200, then change it to 1,200. So keep the minimum mass range that you need, and that will really simplify the data and make it easier to find your things. So that's something easy to change, right? You just come here and change the mass range. Very simple. As you saw when I built these methods, I just asked you the mass range and I typed it, right? So that's a very simple change that you can make yourself. Now, the other change that I would suggest was in the IDA settings, right? So in the IDA settings, here, we talked about maximum candidate ions, we talked about threshold, and we talked about exclusion after a certain number of occurrences for a certain number of seconds. Now, the only case where this came as a problem was the isomer case of the triazines, right? All the other data we looked at, you saw we had great MSMS. It was only in the second isomer of the triazines that we had a problem. So I think we went over that enough. I don't need to go go over it again, how to deal with that. But these settings in this blue box, definitely you can play with. Keep in mind that if you do change the number of candidates, that will affect the final because this is actually the number of scans, right? So if you do go deeper into your sample and you do 20, now you're doing 21 scans per cycle, and your cycle time went up. Even with R peaks, you will now have really triangular peak shape. So I wouldn't recommend too much playing with the candidate items. But I think beyond the mass range and beyond the settings in this blue box, in terms of methods, I think you're set to go, at least for the first week. Of course, it's your instrument, and you can change settings as you want and see how you do. But I don't really see that there's something missing here. The methods we have are really a-okay. If you do change the source and gas parameters, please go back to the lecture and make sure that you understand those couple slides where we talked about the source and gas parameters. That is really the only settings that you can change that you can actually damage something. So if you do not have the right settings in source and gas, for example, if you turn these down for some reason and you have too much flow, then you can cause a flood in the ion source. So that's the only reason, that's the only place where you can really go wrong, and there's no warning message to tell you or something like that. Everything else, if you type a wrong voltage or if you type something wrong in the mass range or something, it'll tell you, hey, it's not right. And then I guess the last thing to say about method development is please use the save as, because as you see, the methods I've made for you here are really good methods and they work nicely. So I would like you to keep those as a template. And if you do change something and something goes wrong and you don't like what you see, you have these methods here that you can go back to. So please use the save as, and just be aware, if you click here, you save. You have to really click on the white arrow to get the save as. Otherwise, this is a save button. So that is a little tricky. I don't like that too much. You have to click on this arrow and hold the save as. Does that make sense? I hope I'm not being too strict there. But I think at least for the first week, I wouldn't focus so much on the method development.
There is a button under the save is a lock method. If we lock the method, we cannot save it at all. We cannot edit it.
Oh, yeah, I'm not sure. I haven't used that. I was even looking, that might be new in this version. And to be honest, I haven't done a X500R training in a while. Save, lock the method. The method will be saved. Okay, let's try to see what happens. Lock test. Now it's locked. So maybe we try to change something and save. You see, it won't let you change it. It'll always let you do save. It'll only let you do save as. Okay, you want me to lock my methods?
It's a good option.
Okay. That's very strict. Yeah, I guess I like that anyway. That was not there in old versions. So how will I do that? I will come to MS Method, and I will open the TOF MS, open, and then I will say lock. Now, can I overwrite? Save. Yes. Okay, so it comes locked. Now open. So don't freak out, guys. You can still make changes. You just have to do save as. Okay. Lock method. And this was my IDA. Oh, what happened? Oh, it's just very slow. Uh-oh. Oh. So, all right. All right. Okay, now save walk. That's the swap. Save. Yes. Okay, cool. How about the LC methods? Can we do the same? So this is the 400 microliter one.
I have a question concerning when you change the flow for the HPLC. You shouldn't increase the timings.
Yeah, I was thinking about that, but I think we have enough time because I over-calculated by a lot the equilibration. So basically now, so we calculated the column volume, right? So the column volume is the radius, which is 1.05 squared, times pi, 3.14, times the length is 100. So the column volume is 346 microliters, 346 cubic millimeters, and 1 cubic millimeter is a microliter. And we are running 400 microliters a minute, which is one column volume, and we're running it for 5 minutes. So we have at least 5 column volumes. So I think it's going to be okay. For sure, your retention time will be different, but I think the same gradient will be okay. You agree?
Yes. For the Tony's sample, let's say he had a retention time of 14.5 or 15, and a little bit of noise afterwards. So I don't know if on 0.4 it will be the same, or the retention time would be a little bit more.
Well, I don't think the retention time will change that much because we are still changing the gradient, right? So hopefully the stuff will come off at the gradient. I mean, here is a peak coming at 17 minutes, which is okay. I think his stuff has noise because it has noise. Why don't you try it and see? You're not going to run, I mean, don't run all the samples again, right? You're going to make, we'll talk about that now, what samples you want to run. But try it and see, and if you have to, come here and adjust the gradient. Don't forget, you have to change the stop time in 3 places. So you adjust the time here, then you have a stop time here, and then in the MS method, you also have a stop time.
Yes, correct.
So you have to change, and you see all my methods are labeled with also the stop time, the method duration. So if you do change the time, you gotta type it in those 3 places.
Alek, what happens if the stop time is different from one method to the other, from the LC to the MS?
Well, nothing, I mean, there will be no issue or anything, just the other device will wait until that one finishes. So if you have your MS method 10 minutes and your LC method 15 minutes, the MS will collect data only 10 minutes. The LC will continue for the next 5 minutes, as it should, and then the run will finish, and then the next run will start.
Okay.
So each piece waits for the longer piece, let's say.
I just noticed when you locked the methods, I also noticed a button where you can also unlock. Is it easy to unlock, as easy as you lock?
Never locked before, and I never unlocked before, but we'll try it right now. I'm also curious. I'm just going to delete that rubbish thing I made. Okay, so let's open, and open, and open. Probably it's easy, and then you can remove remove that permission from some people. Where was it? Save, let's say unlock. Yeah, it's easy.
Okay, so there is no password
At least
option or something like that.
No, doesn't seem to be. Probably there is a whole security thing you can set up and everything. And probably in that security, then maybe the administrator can lock and unlock and the users cannot or something like that. But you guys are a research organization. I think you don't want to fool around with all that stuff, right?
Actually, we prefer methods to be locked and every user to build up on these.
Right. Okay. I mean, we can set it up, but the problem is then, you know, the security is more designed to go with like GLP and pharma companies and so on. So I think you will become more frustrated with it than it will actually help you in your environment, because you cannot, like a user has rights or they don't. It's not like they can go to another project and have different rights. So here you have user management, and you can set that up if you want. Everyone has a password and logs in and so on. But I think consider that really if you want to do it or not.
All right, no problem. Actually, I have a question for you, Alek, as well. Is there a warning that the machine would give us if, let's say, one of the solvents runs out, like what happened with us yesterday, or the wash solution on the autosampler also runs out? Does it give us a warning, like a visual warning on the machine or on the software as an error or somewhere?
Unfortunately not, no. There is no solvent counter in this LC. I know some LCs have that. You could put a minimum pressure, but I think you'll be more frustrated by that because it may go off at the beginning when you're trying to pressurize. So unfortunately in this LC, there is not that feature is not available.
So we always need to have an eye on the solvents before starting.
Yes. Yeah, always calculate how much solvent you need for your run and then check that you have enough and make sure that you can see the bottom of those bottles. Like I said, they sit in that rack and you can't see the bottom. But you'll get the hang of it. We'll see, and then it'll become second nature. Like you said, go ahead and run, of course, whatever samples you want, and I think, have some fun tomorrow and next week. But personally, what I would like to say is that maybe you can run some of the samples spiked again, and you can spike in less triazine. So try to spike in 10 times less, and then try to spike in 50 times less and 100 times less, and go through the exercise that we did and see if you can find the triazines, both in the targeted and the non-targeted. You may think, okay, that's kind of silly, but if you do that exercise, not only will you be looking for lower concentration things, but that will also familiarize yourself with everything in the software that we did. And I guarantee you, if you don't do that, then you won't remember where the software, and then when you come back to the instrument after 2 weeks or 3 weeks, you'll be frustrated. So you could do that, and then you can also run Tony's sample 10 times diluted and see if the mass accuracy changes and see if you get a better formula. Because one of the reasons we might have gotten stuck there is that sample was so saturated that at that high level, the mass accuracy is affected. So you could try a 10x lower and a 100x lower. And I think that's a legitimate workflow anyway, because your goal is to identify something, right? So now you've identified it. Now you can dilute the sample and run again, and now you know what to search for. So maybe that will not come up so nicely as the first hit in the non-targeted, but it doesn't matter anymore because now you know it. And then you can try to get some better fast accuracy results, because I think E8 counts is really kind of pushing it a little bit with a high signal there. So that would be the two sets of samples I would recommend. Spike your samples again, triazine's lower amounts, and then run that sample from Tony again at a lower dilution, or higher dilution, lower concentration. But does that make sense?
Yes, sure. Also, we have in the samples we're gonna prepare by Zahra. She's with us here. She also has standards that she would also like to run with along with her samples. So we're gonna also spike those as well, right?
Okay, great. Yeah, that sounds great.
Yeah.
Just keep in mind, you know, the concentration range we are looking at here is somewhere between 1 and 100 ppb.
Yeah.
So try not to be lower than that, and try not to be higher than that. I don't know. Did you want to do quantitation? Because this week actually we didn't talk about quantitation. But if you want to do quantitation, you have to run a standard curve.
Yeah, maybe we'll try to do that.
Yeah, that would be great.
With
so you can run a standard
Zahra,
curve
yeah.
next week,
Yeah.
and then I can show you how to do the quantitation on Wednesday and Thursday. That could be something as a plan to do that we didn't cover.
So it's just normal, like right? But just by setting up different concentrations and putting them in the batch,
Exactly.
right?
Exactly.
Yeah.
Just different concentrations. Yeah. So
Alright.
you can do like, you know, I like to do, you know, 1 nanogram per mil, 2, 5, 10, 20, 50, 100.
All right.
Something like that is a good range. You can use the triazines if you want, or you can use the other compounds that you were just mentioning.
All right.
Obviously, has to be something you know, right? Quantitation is from something known.
Yeah, we can do both, maybe.
Yeah.
All right.
All right. So I think that brings us to a close. Any other questions? Any comments? I hope you found it worthwhile. It was not too slow or too fast. Anyway, don't worry. We'll definitely be in touch for sure next week, and then I will be on break for 2 weeks. Christmas break. I'll take some vacation, and then we can return in January, of course. So definitely, we're going to be in touch as you start to get the instrument. All right. No one has any questions or anything?
Perfect, Alek. Thanks a lot.
Okay, yeah, sure, you're welcome. So, yeah, it was my pleasure to work with you all this week. I really enjoyed it. And I hope you see really how cool the system is, how much you can do with it. So I wish you good luck tomorrow and on Monday and Tuesday. If you do have some emergency or something, you know, just send me a quick email and I'll try to join you for a few minutes. That could be possible Monday and Tuesday if you need. And then otherwise, yeah, also have a nice weekend, and I'll see you on Wednesday.
Sure.
So Wednesday at 9:30.
Sure.
I'll send you the Teams invite.
Perfect. Thanks a lot, Alek.
All right, you're welcome, guys. Take care.
Have a nice weekend. Take care.
You too.
Take care, Alex. Thank you. Bye-bye.
You're welcome. Okay, bye, guys.
Thank you, Alek.